开始。
你等一下哈，快5点，你那边打开嘛？
哦，
你把它打开，然后看看，快轮到我的时候，
这就是那个嘛 ，Antonio。
快轮到我的时候，来上。
Hello，
点的时候你再上。
像，
我不知道，应该是在这个地方。
可是我的视讯，我没有关掉哦，是刚你按的。
对，
都不用关掉。
荧幕
人很少。
Okay. Can you hear me now? Hello, everyone.
Yeah.
我也是，可以看。
Just a second.
So I'm ready, and
yes,
all of us are almost ready.
Okay.
Started.
Okay. We can start. Just 1 minute of introduction, and then we will start the opening the ceremony with other chairman. Now I give the technical details. And we start the YouTube live streaming.
你那边打开你就知道，我在之前是 Antonio， 那 Antonio 他讲快完的时候，你再上来，他大概就是他大概是4点40开始讲。你先看，打开看你们看得到。
Okay. No, dove a schermo intero. Welcome to the Italy-Taiwan bilateral meeting on emergent crystalline materials, co-organized by University of L'Aquila, the Ministry of Science and Technology of Taiwan, the Taiwan Consortium of Emergent Crystalline Materials, the Representative Office of Taipei in Rome, the Italian Economic Trade and Cultural Promotion Office in Taipei, and the Italy-Taiwan Scientific Exchange Association. It is a big pleasure for me, on behalf of the whole organizing committee, to open these 2 days of scientific talks, which will be held on the Cisco WebEx meeting platform. There is a live YouTube broadcast of the whole event. Moreover, we have prepared a virtual interactive showroom with supporting materials on this event on the Padlet platform, with 25 virtual stands from 20 institutions, with over 200 posts with videos, posters, scientific papers, link to websites, and even a podcast contribution. Please visit the Padlet wall and post comments or questions for the various delegates of this bilateral meeting. Thanks to the capabilities of the Padlet app, a new form of communication in scientific meetings can be explored, also with your help. This virtual meeting aims at providing a forum on new trends in material science from the Italian and Taiwanese scientific communities. The scope is to gather physicists, chemists, engineers, and material scientists working on innovative materials and their application in both countries. The scientific program will feature selected talks related to topics covering advanced materials and related applications in photonics and optoelectronics, energy conversion, water treatment, green technologies for sustainable growth, surface science, semiconductor industry, and nanotechnology, with the participation of invited speakers of highly reputed institutions of both countries, leaders in their respective scientific field. We hope that this event could further stimulate bilateral cooperation with new collaboration and international projects. Enjoy this meeting on WebEx, YouTube, and Padlet. But let's start now with the opening session with Chairman Maurizio Peruzzini from CNR in Florence. Maurizio, the stage is yours.
Thank you, Antonio. Thank you for your words. And good morning, ladies and gentlemen, magnifico rettori of the University of L'Aquila, ambassadors, colleagues. So it's really a pleasure for me to introduce the first talks, the first speech of the morning, which will be delivered by ambassadors Andrea Singh Hing Lee, that is the representative of Taiwan in Italy. Please, Dr. Singh Hing Lee, the stage is yours.
Thank you. Good morning and good afternoon to you all. It is a great pleasure for me to join Deputy Minister Dr. Lin Minchong of Science and Technology of Taiwan. I'd like to say my greetings to my counterpart, Minister David Gio of Italian Economic Trade and Cultural Promotion Office in Taipei, Rector Magnific Eduardo Alessi of University of L'Aquila, distinguished guests, professors and researchers of all participants at the Taiwan-Italy bilateral workshop of emergent crystalline materials. As a representative of Taiwan in Italy, it is really a great honor for me to be invited to deliver the opening remarks of this two-day online workshop. The bilateral relations between Italy and Taiwan has always been very dynamic. Our representation, which celebrates its 30th anniversary this year, has continued to work on promoting ever closer ties between our two countries in commercial, agriculture, academic exchanges, and collaboration in a diversity of fields. In fact, we have recently created the Culture Division in Taipei Representative Office in Italy, 1 year ago exactly, to further expand the horizon of culture exchanges with direct support from the Taiwan's Ministry of Culture. And as chief of the mission in Italy, I look forward to working harder to try to get also in the future technology division in our representative office in Rome. And that will be very important and instrumental in the future science and technology exchanges. Trade-wise, Taiwan is currently Taiwan's 5th trade partner in Europe, with the main Italy products ranging from machinery, cars, food, and fashion being highly appreciated in Taiwan market. At the same time, Taiwan is also among Italy's top 5 trade partners in Asia. As many of you should have been aware of, Taiwan's economy has continued to thrive throughout the COVID pandemics and enjoys an economic growth rate of approximately 8% in the first half of 2021. The importance of Taiwan as indispensable trade partner to Italy and to the world has also been widely recognized when car manufacturing industry around the world turns to Taiwan's world-leading semiconductor industry in the hope of solving the crisis of the shortage of microchips, which the shortage problem is still pertain and is lingering, and we don't see an immediate solution. So the crisis and the challenge is still there. So without doubt, the powerhouse behind Taiwan and Italy's highly advanced industry and technology is our shared tradition of quality higher education and investment in research and development. In these couple of years, I have personally witnessed the dedication of academics and the researchers during my visit to universities and research centers from north to south of Italy, from Turin to Milan, from Rome to Naples, It was indeed a delightful surprise to discover that besides the research projects under the frame of the National Research Council of Italy, the CNAI, and the Ministry of Science and Technology of Taiwan, which has already led to many successful joint research projects, there are many more scientific exchange and research collaborations going on, like this one of today's workshop. This phenomenon has inspired my team to further seek to establish bilateral cooperation framework for agriculture technology research, for example, and to support the founding of a newly reality in Italy, the Italian-Taiwan Scientific Research Association, with the help of Professor Stefano Pelagi from La Sapienza University of Rome, in order to provide more resources and enhance networking among scientists in both countries. I believe with the joint efforts of governmental and the research institutions, together with the strong will and professionalism of research personnel, I'm confident that Italy and Taiwan's pursuit of excellence will not only contribute to the industry of our two countries, but will further benefit the human beings as a whole. The Taipei Representative Office in Italy, as the government representative office of Taiwan, Italy, will continue to offer our support wherever and wherever needed. So, before concluding, I would like to express my gratitude to the chairman of today's workshop, especially Professor Antonio Politano, for your effort in coordination. My sincere wishes for a very successful event and best welcome to each one of you. Thank you very much.
Thank you, Ambassador, for your speech and for your good words. And let's say good afternoon, I correct myself, because the time difference is still operating. Well, so I give the stage now to Ambassador David Giglio, that is the representative of Italy in Taiwan. Please, Ambassador.
Thank you, Professor Peruzzini. I'm very grateful for the invitation that I've received to participate in today's virtual meeting. Grateful especially to Professor Politano for his efforts in coordinating the preparation of this today's event. I would like to extend my greetings from Taipei to Ministry of Science and Technology here in Taipei, and to my counterpart, Andrea Lee, at the Taipei Representative Office in Rome. As he has rightly pointed out, Italy and Taiwan do entertain a robust relationship, especially in trade and culture and human people-to-people exchanges. I believe that there is an ample latitude for improvement in the area of scientific cooperation. Both Italy and Taiwan are endowed with a lot of potential in this field, and they have until now punched below their weight, I should say. It is, of course, in our mutual interest to increase the contact surface between the mutual scientific communities. And I believe that today's and tomorrow's event goes in the right direction. Despite the pandemic, the frequency of the interaction can be further heightened. And when conditions will be such that traveling between Italy and Taiwan can be again safely entertained, I believe that there will be a rebound in many areas, certainly in trade and cultural exchanges, but also, I hope, in scientific and technological exchanges. In this regard, I would like to offer my congratulations to Professor Pelagi and of the University of La Sapienza, because with this initiative of creating a permanent platform for exchanges, academic exchanges, ITA-SEA, he is doing a very good service for the promotion of interaction between the two scientific communities. As Italy and Taiwan, I think I believe we have a challenge. We are perceived as a country of mechanical excellence, not necessarily as a country of technological excellence. This is probably due to an imperfect knowledge of all the areas where Italy does excel, and the fact that this year the country has been awarded the Nobel Prize in Physics is actually a very positive news for Italy, not only in Taiwan, but I should say worldwide. It showcases the eminent position that Italy has in some scientific areas. It has been pointed out that there is a framework for cooperation that's provided by the interaction between the Italian National Research Council, Consiglio Nazionale di Ricerche, and its Taiwanese counterpart, National Science Council of Taiwan. In 2011, a memorandum of understanding was signed between the two parts, and some areas of cooperations were identified, such as biomedicine, smart cities, cybersecurity, green energy, precise agriculture. And some activities have taken place in this past 10 years, and many more, I think, should be in the pipeline with the support of the institutions that oversee this type of cooperation. I believe that the scope, the subject matter of the seminar that will take place tomorrow, today and tomorrow, deals with an area where Italy and Taiwan can do concrete cooperations. Materials, especially high value and high technological materials, are used in high-end production lines, and one of them is, for instance, that of the semiconductors. So I think that by highlighting the potential links between Italian and Taiwanese technologies and the industrial supply chains, we will take an important step in the common effort in the redefinition, in the reshaping of global supply chains that are undergoing a monumental change in these times. So all I can say is that I think that the conversations that will take place between academics and scholars of Italy and Taiwan today and tomorrow online will certainly be instrumental to the further goal of bringing together Italy and Taiwan, who have already taken together important steps, but they can do a lot more by joining forces and resources in the scientific and the technological realm. And as my counterpart has highlighted, also my office stands by offering any support that can be useful to promote and facilitate exchange between Italian institutions and local counterparts. So even after today's and tomorrow's event, please do not hesitate to contact this office for exploring potential cooperations between Italy and Taiwan. Thank you very much.
Thank you, Ambassador David Giglio, for the nice words and for the presentation of the many possibilities existing to strengthen the relationships between the two countries. Now, I give the stage to the to the ministry, Min Song Lin, that is the Deputy Minister of the Ministry of Science and Technology of Taiwan. Please, Ministry. Is the ministry connected? We cannot hear you. Antonio, I think there is a technical problem. Can you hear the ministry?
we can give the stage to Professor Alesse, Rector of University of L'Aquila.
We skip for the moment the presentation of the Deputy Minister Min Song-Lin, and we move to the magnificent Rector of the University of L'Aquila, Professor Edoardo Alesse. Please, Rettore.
Thank you. Good morning.
With us today.
Everyone, and many thanks for inviting me. It's a great pleasure for me to bring the greetings of L'Aquila University, my personal one, on the occasion of this first Italia-Taiwan meeting, bilateral symposium on innovative crystalline materials and their application. It's a very important topic and a truly interdisciplinary field of study to which physicists, chemists, engineers, biologists, and biotechnologists can contribute and meet each other, interact with each other. This type of study could be very useful for modern societies and could have an important economic as well as scientific impact in photonics, in nanotechnologies, in particle physics, but also in the field of semiconductor and sensor, and finally in diagnostic and therapeutic medicine, improving the discovery and treatment of important diseases such as cancer. Now I want to address special greetings to Andrea Xing-Yin Li, Ambassador of Taiwan Rome, David Giglio, Chair of Economic, Trade and Cultural Promotion Office of Taipei, and Min Song-Lin. I don't know if the minister can hear me, but I want greetings to Minister, Deputy Minister of Science and Technology of Taiwan. I will not be able to stay as long as I would like with you during this meeting, but because of previous commitment, but I'm sure that an excellent job will be done, thereby promoting the advancement of this area of research and the interaction and the collaboration between Italy and Taiwan. And this is very nice, very good result for all of us. So now I stop my presentation and just wish good job to all of you for this beautiful meeting. And I want finally thank Antonio Politano for organizing in L'Aquila this important scientific meeting. Thank you very much.
Grazie, magnifico Rettore. Thank you very much for your kind words and greetings. And I would like to try to come back to Deputy Minister Min Song-Lin, should he be in online.
Good morning and good afternoon. Our
Good
honorable
morning.
guest, Minister Plenipotentiary David Giglio, Professor Alesse, and Ambassador Andrea Xing-Yin Li. Dear fellow scholars, it's my honor to give an opening message for this meaningful workshop. In the event of the current epidemic, we have to adapt an online symposium, and I thank you very much for your participation. Ministry of Science and Technology of Taiwan, MOST, in the past decades, continued to support and connect academic and industry research. It's our responsibility to formulate policy to reinforce the frontier technology, such as emergent materials, and also to help address environmental, social, and economic issues. Italy and Taiwan have a long history of good economic and trade relations. The cultural connections, political relations, and the general friendship between Italy and Taiwan have grown closer. Scientific and technological cooperation and exchange activities provide opportunities to promote a better level of partnership. Through the symposium, we look forward to enhance the network between the Italian and the Taiwanese researchers, both in academic and the industry institutions, and to enhance the synergies between the two countries in the scientific and the technological field to an excellency. As the Deputy Minister of MOST and the Condensed Matter Physics, I acknowledge the committee for achieving this workshop during the pandemic and hope the fruitful cooperation between Italian and the Taiwanese science communities. I wish you all a wonderful day. Thank you.
Thank you so much, Ministry. And so after this first round of presentation, we continue the morning ceremony, moving to Professor Hing Hier Cao from the National Taiwan University, who is director of the Center for Emerging Materials of that university. Please, Professor Cao.
Can you see my screen?
Perfectly. Please go ahead.
Yes, yes.
Okay. Good morning, good afternoon, everybody. So my name is Xingzhe Gao, and I'm actually a condensed matter theorist, but I'm here as a convener of Condensed Matter section of physics panel and the director of TCECM. To give you some, to give the Italian friends some short introduction to the condensed matter physics research in Taiwan. First of all, I would like to show you a pie chart, which is to give you a roughly idea of the funding for physics for basic research. And as you can see from this chart, so there's more than half of the research funding for physics are going to a broad range of condensed matter physics. And in particular, there's a big portion of the funding going to, say, semiconductor physics, magnetism, optoelectronics, and surface science. I apologize that I didn't convert this in euro, but basically just divide by 3, you'll get the number. So in terms of condensed matter physics, so the total budget for personal grant is about 60 million euro, and those are distributed among 340 principal investigators in about 30 to 40 universities and government labs. So as you can see, we are a relatively small community compared to Europe. In addition to these personal grants, there are special programs. One of them is this TCECM. So basically, I'll explain what the acronym means. So annually, we have about 2 million euro budget. Recently, because of the trying to go beyond the Moore's law, the government initiated a Angstrom Semiconductor initiative, which is the annual budget is roughly 4.5 million euro. So I'll give you some background of these two special programs. I have to emphasize that the personal grants are for freestyle exploratory kind of research, but these special programs, we have missions. So these are mission-oriented research. So the first one is a TCECM. It's an acronym for Taiwan Consortium of Emergent Crystalline Materials. It was established more than a decade ago. So basically, it's recognized Taiwan needs the ability to grow our own crystals. And basically, we integrate the studies in different material science centers and try to emphasize the the single crystal and thin film epitaxy. Okay, and we want to use this platform to cultivate next generation research and design talents and train senior technical personnel for these solid state materials. We want to be able to produce special high quality single crystals and new materials for both basic and applied research. We also want to strengthen Taiwan's technique to fabricate cutting-edge materials and facilitate Taiwan's specialty development of single crystal growth. On the application side, we want to assist the company to increase their international market share through patent licensing and technology transfer. And we want to have our own single crystal growth capability. And as you will see, many of the invited speakers from Taiwan are part of this program. The most important message for the mission for this program is we want to make materials from Taiwan a well-known brand, and we want to set up the world-class academic research programs, and we want to support the develop a new material needed by the Taiwanese industry. So this TCECM, you can think of it as a platform for material innovation from Taiwan. So there are several goals we want to achieve. We want to encourage through material growth. We want to encourage cutting-edge crystalline material growth. We want to develop internationally competitive academic research programs. And we want to also establish close links to industrial applications in order to create added value economy for Taiwan. So let me move on to the second initiative. So this initiative is called the Armstrong Semiconductor Initiative. Basically, this is due to a recognition of if you keep shrinking the size of your transistors, then at some point you're going to reach the atomic limit, and a lot of important quantum physics will enter. So there are several thrusts, and the physics part, the physics part, focus on the atomic detection technology, detection technology at the atomic level, and the new material development. So this atomic scale metrology and inspection basically want to leverage the cutting edge metrology inspection techniques such that we can develop some Armstrong scale resolution in academia, and potentially they can have applications for this semiconductor industry. And the emphasis here is we want to have an inline techniques such that ready for the manufacturers to use. And the thrust two is we want to develop key materials for future devices. And so, for example, this how to apply, how to grow large-scale 2D materials, how to put them into devices is a very hard research topics in this thrust. So I want to share with you some statistics from this TCECM program. So TCECM program has been here for more than 10 years, and from the past 6 years, we see that there's a very good publication record. For example, there's in top 10 journals, we have out of all the publication, more than half are in the top 10 first-tier journals, and 12% are in the top 1% journal. And importantly, 60%, more than 60% of these publications are done through international collaboration. And this will be the focus of the next phase of TCECM. We want to strengthen the existing international collaboration and try to bring it to another level. And as I posted on this Padlet, there are certain areas the Taiwanese researchers have some advantages. For example, the 2D materials, graphene related, and also this energy materials, and semiconductor quantum dots, for example, and some battery materials. So these are currently the strength of the PI in this program. And from the key phrase analysis, we see that we see a lot of these like perovskite and topological insulators, monolayer materials, and heterojunctions. So this is, as you can see, this indicates what kind of research the PIs are in this program are interested in. Also, there's a strong link between the industry and this TCECM program. Since 2019, the Taiwan Semiconductor Manufacturing Company, the largest foundry in the world, they provided a type of research fundings to fund the researchers, research scholars to promote the next generation's semiconductor research. Due to this chip shortage, and the TSMC actually is expanding this R&D team to more than 8,000 people, and they're going beyond just optimizing the manufacture processes. They will also fund mission-oriented basic research in order to meet the future challenges. So I'll quickly go through some of the highlights from this TCECM program. So one key component is to produce high-quality single crystals. So currently, there's a lot of crystal has been grown at the various labs funded by this program. For example, one of the single crystal has been become a candidate scintillation crystals for the next generation LHC. So there are materials for quantum storage and fluorescence materials for car lamp. So this is one of the material area that we focus on. Another focus is this two-dimensional 2D materials for electronic and optoelectronic applications. For example, there's the 2D material has been applied to hydrogen energy generation. It has been applied to soft electronic components, and there's some research in the solar cell materials. The graphene is also applied to this solar cell research. Another highlight is that this by designing a special Mica material, one can put the oxides on this Mica material to achieve some very soft, very flexible electronic devices. To highlight the industry and academic collaboration, one of the wafer level boron nitride was grown through the collaboration between the researcher from this TCECM program and TSMC. So with this, I will like to conclude. In the next few years, we want to hope to strengthen our international collaboration through this TCECM platform. And we want to change the slogan from materials from Taiwan and to material from Taiwan to the world. And I hope that through this meeting, more collaboration can be established and more joint research will be started. And with that, I thank you for your attention.
Thank you so much, Professor Herr Cao, for this, let's say, great overview of the potentialities and the realities of what Taiwan scientists are doing in the area of condensed matter. So I think that there is time for questions or curiosities raised by the audience, and so I encourage people to raise questions to Professor Cao. Please. Is there any questions? Maybe Antonio can help me looking if some questions are present. I just started with a curiosity. I am personally working in an area related to what we are presented, that is 2D black phosphorus, exfoliated black phosphorus. And I am wondering if this kind of, let's say, intriguing 2D materials has been object of studies in Taiwan, and there are group of scientists in Taiwan working on this fantastic material.
I'm not sure I know anybody who's working on black phosphide, but I can be wrong because as a theorist, I roughly know who works on 2D materials, but specific platforms,
that could be of interest, just to let's say in a separated time, just to talk about this, because that could be interesting, just also for start collaborations.
Yeah, I think that material, from what I know, is very hard to grow.
Yeah, the problem is the stability of the material, indeed.
Yeah.
But
that's what I recall.
The electronic properties are really spectacular. Well, is there any other curiosity or question? Please do not hesitate. In the audience? Okay.
There's
hello.
No. If
you hear me?
Yes, I can hear you.
Okay.
Please introduce yourself when doing the question, or raise the question. Professor Carlo Rizza, please.
Sì, from University of L'Aquila. Good morning or good afternoon, everybody. Okay. I see in one.
Can you speak loudly, please?
Sì.
Grazie.
In one of your slides, I see some word metamaterial. I am a researcher on this field. Can you give some details about your activity in this field, please? Do you understand my question?
I didn't catch the last part, the last sentence. Could you repeat?
Can you give some detail about your activity on metamaterials? Do you
metamaterials
them, or there are some activities about this field? Are there?
Yes, as far as I know, there's a couple of researchers doing metamaterials. I think one of my former colleagues was doing it, and there are some people from the engineering side that they're also doing it. Yeah, so actually, I think there's probably 5 to 10 TIs are doing metamaterial research. But I think I have to get back to you on the exact numbers and the context.
Okay. Thank you.
Thank you.
Is there any other question? I don't see anything in the chat. Okay. If this is not the case, I would like to thank Professor Hin-Kier Kao again, and to move to the next speaker with Stefano Pelaggi, Professor Stefano Pelaggi from the University of La Sapienza in Rome. Professor Pelaggi will talk about the ITASIA, that is the Italy-Taiwan Scientific Exchange Association, and we are very eager to know something more about this project. Please, Stefano.
Thank you, Professor Perazzini, and good morning and good afternoon to the honored guest. I'm really glad to be speaking here today. I am a political scientist, so for one time it's really nice to be in between real scientists. And I am here to present this newborn association, which is ITASE, stands for Italy-Taiwan Scientific Exchange Association. I'll try to show you some slide. I think you will be you seeing them now, right?
Yet? Apparently it doesn't work for the moment. Okay.
So the association is a newborn association which aims to connect the world of academia, between Taiwan and Italy in the technological and scientific sector. So basically, we aim to connect, to enhance, to develop the cooperation between the two countries. The main objective is an circulation of intellectual human resource and talents, deepening the excellence in the field of science and technology. So particularly, we are focusing on medicine, information technology, natural and mathematical science, and engineering. We did the association will be structured as so. We did choose a president, which will be Professor Roberto Verna, which is a full professor of clinical pathology at Sapienza University of Rome. There will be a board, and there will be a scientific committee. Until now, we already have 50 person inside the scientific committee, and while doing so, we started to recollect all the already existing relationship between Italy and Taiwan, and it was really fascinating because we did find that there are a lot of universities which have been cooperating in so many different fields. One of the most remarkable example is the conference we are here today, and the relationship with the University of L'Aquila as established with Taiwanese University.
Stefano,
so we did.
Stefano,
Yes.
sorry, but we don't see anymore your presentation.
Oh yeah, I just took it out. Just wanted to show you the logo and so on. So it's
Okay.
I thought that it was it would be a little bit more communicative if we don't have. So we did find a lot of synergy, a lot of cooperation between the two countries, and this is exactly what the association aims to do. So to use this ITASEA as a framework, to use ITASEA as a tool to promote cooperation. We all know that the past 2 years have been difficult for everybody, and even for the academia. And international exchanges have become more and more difficult. This is even more true in the case of the Asia Pacific. Countries like People's Republic of China, Taiwan, Japan, South Korea did choose a way to face the pandemic, which kind of closed those countries to the outside world. So, for example, we in Sapienza we did add several agreements and cooperation framework with Taiwanese University, signed in 2018 and 2019, but none of them has been really implemented because everything stopped for those 2 years. So exactly, this is one of the place where ITASEA could really work. So try to revive, try to give back life to all those agreements which were done, which are already in place, but are somehow suffering from all the consequences from the pandemic. And we did receive the support from the Taiwanese representative office in Italy and the Italian representative office in Taiwan. I would really like to thank Ambassador Andrea Singhilli and Ambassador Davide Giglio for the words that they spent today for the association. We did receive the support from the Italy-Taiwan Interparliamentary Friendship Group, which is the main organization which is trying to support the so-called Taiwan cause in the Italian politics. It's a group which can count on more than 100 between deputy and senator in the Italian politics. We received support from ECCT, which is the European Chamber of Commerce in Taiwan. And we can count on the, several members of the Italian community residing in Taiwan, which mostly operate in the field of technological and scientific research, most of them in information technology, but lots of them are even professors in different Taiwanese universities. So it's exactly what Ambassador Giglio meant for people-to-people cooperation. We are, with ITASEA, we will be trying to use all those dots which sometimes are connected with Taiwanese and Italian reality, with Taiwanese and Italian research center and academia. We would like to put all those dots together to create a big network, which could be a really useful tool for the scientific and technological cooperation between the two countries. country. In the near future, we will be registering the association in the next week. In the near future, we are planning to open and to create a similar association under Taiwanese law. So it will be really important to have a counterpart with the same exact scientific committee which can operate in Taiwan. At the same time, we are trying to create a database of all the academic exchange and cooperation between Italy and Taiwan. And again, I would like to stress out how many of them there are. And so it's really important to know, to have a precise knowledge of what those agreements are and how they are implemented. There are a lot of agreements, there are a lot of student exchange, there are a lot of joint projects and executive protocols. We did find that there are at least 3 double degree courses already existing between the two countries. So ITASEA will try to build a structure which is capable of connecting research center, university, single researcher of the two countries to facilitate joint projects. But we do even try to put inside this framework companies. For example, until now, we did find a lot of interest from biomedical and pharmaceutical company in Italy and information technology company in Taiwan. So we do strongly think that an association like ITASEA could be an important actor to develop this cooperation. And more than everything, we would like to create the condition to encourage student exchange between the two countries. We do all know how exchange works. If we do have a flow of Italian student to Taiwan and Taiwanese student in Italy, everything grows. Everything gets better. It's the people, getting to know each other. Today there are students, PhD students. Tomorrow they might be a faculty member. There might be professor and researcher traveling back and forth in the two countries. There are a lot of agreements and memorandum of understanding. We did find that sometimes some of them are kind of hard to implement. And the last, one of the last, but probably the most important thing that we will be trying to do is to create a newsletter and, of course, a website in which we will write all the information on professor and student exchange opportunity, all the deadline for funding from institution of the two countries, the deadline in for participating in individual and collective calls. There are so many ways to promote and so many ways to finance student professor exchange, joint research. A lot of times academia and professor in both countries doesn't know about that. So we will be really trying to do this, and the support of the Taiwan office in Italy, under which the idea, the same idea of ITASEA came out during a meeting with Ambassador Andrea Singilli. It's so the support of the Taiwan office in Italy is really important, as is the counterpart in Taipei. So we will be we do really hope that we will be able to give a new push to the already lively relationship between Italy and Taiwan in the scientific and cooperation field. You all have my email, and I do remain available for any kind of comment. Of course, you are all invited to participate in the association, and I would like to thank Professor Politano for showing us how to do things, because this is exactly the kind of activities that we would like to support, we would like to promote, and we would like to create in the next month and in the next year. Thank you very much.
Thank you, Professor Pelaggi, for your very brilliant presentation of what ITASEA is doing and what ITASEA would like to do in the next time, that I think is even much more important. To strengthen the relationships between Taiwan and Italy will be your goal, and I guess that you will have success in doing this. Okay, let's see also if there is some curiosities about the activities that you have presented and the perspectives of your activity in the audience. And so I ask people to raise questions, writing in the chat. I see there is something maybe in the chat. No?
I have okay.
Just to add some comments.
Ambassador, please.
Just to say,
you want comment?
No, just want to say my gratitude to Professor Stefano Pelaggi in accepting my proposal, together with also the good blessing from my counterpart, the WGO. We look forward to your good job, and I promise to organize a party to celebrate the creation of the ITASEA. So don't let me wait too much. I know you have been working very hard. So good job, and see you soon on this particular endeavor, the success of it. Thank you.
Thank you, Ambassador.
Thank you, Ambassador, for this nice, let's say, words. And maybe Antonio would like to comment or say something about?
Yes, just a comment. A good initiative to promote the Italian-Taiwanese cooperation could be the constitution of virtual joint labs. And this workshop is also designed. I hope that at the end of this symposium we could present an agreement for a virtual joint lab on advanced semiconductors. And I have also curiosity for Stefano, if he could spend more words regarding the panel of the ITASEA association in order to illustrate the Italian and Taiwanese institutions which are already involved in this important initiative.
Yes, thank you, Antonio. Yeah, well, as I said, the support of the both representative office is essential. The same idea of ITASEA came during a meeting with Ambassador Andrea Singilli and some professor of Sapienza. So this is an association which start directly under, allow me the word, the umbrella of the two office. We are based in Italy, so this part, the ITASEA will be working a lot with Italian Academy, and I think that the work that we have done collecting all the existing agreement between Italian university and Taiwanese university is really important, because some of them started from people to people. So there were some professor which met other professor at a conference. They started a very lively and a very long-standing cooperation. So what is the aim of ITASEA is to bring those work, those cooperation in broad daylight, and try to use those connection, those synergy, that cooperation in order to promote more and more cooperation like this. So I think it's a really it could be a really important situation, because having the support of the Taiwan representative office in Italy, of the Italian representative office in Taiwan, the Italy-Taiwan Parliamentary Friendship Group, the European Chamber of Commerce in Taiwan, we could be able to have a powerful tool which sometimes could help even in redefining, in shaping the law and the legal framework which regulate the academics exchange and the scientific cooperation between Italy and Taiwan. We do now have a new law, a new legal framework for Taiwanese students in Italy, which can receive a grant thanks to the work of the Taiwanese representative office in Rome, and so everything. All those structures need to be implemented, and this is exactly what can implement this. So meeting, cooperation, having more and more students, more and more researchers and professors to be in contact and to be ready when in a few months we do hope that there will be renewed possibility to travel between Taiwan and in Italy, and at that point we do hope that we will have a really complete framework to start a really solid scientific and technological relationship between the two countries.
Okay, thank you. Quite exhaustive. Is there any other question?
Just another comment. Congratulations for the nice virtual stand prepared by Stefano on that platform. So I invite you to visit it. There are very interesting news also regarding the story of Taiwan with a very nice podcast.
Yeah, I confirm. That's quite interesting indeed. Okay.
Thank you. So thank you very much.
Please. Who is speaking?
No. I was thanking Professor Politano.
Okay. We thank Professor Pelagi then for his brilliant presentation, his enthusiasm in strengthening the relationships between Italy and Taiwan, and we think that something more will happen in the future. following the guidelines that you have presented, and following also the important cooperation with the two representatives of Italy in Taiwan and Taiwan in Italy. Well, let's move to the next speaker, which is Professor Antonio Politano from the University of L'Aquila. Antonio, I know Antonio since, let's say, 5 or 6 years, and I have seen the last part of his brilliant career, and he's really an eclectic scientist. And let's see what he's presenting today. Italy-Taiwan cooperation on science and technology on advanced material. Focus on surface science with layered materials and novel topological phases of matter. Antonio, please, the stage is yours. We are perfect in time. Let's try to keep the schedule correct. Please.
Thank you, Maurizio. I'm Antonio Politano, and I will present some milestones of the Italy-Taiwan cooperation on science and technology with advanced materials, with a focus on surface science with layered materials, mostly van der Waals semiconductors, and novel topological phases of matter. In the last years, the number of co-authored papers on material science by Italian and Taiwanese partners is increasing so much. And after the advent of topological materials and two-dimensional materials, this collaboration had a boost. A good contribution in this collaboration comes from surface science, which is an interdisciplinary research field at the boundary between physical chemistry, condensed matter physics, and material science. From the study of chemical reaction at surfaces and interfaces, it is possible to discover the physicochemical mechanism ruling the surface processes at the basis of gas sensing, photocatalysis, electrocatalysis, and so on. Surface science also studies collective electronic excitation at the surfaces, such as surface plasmons, and I will present some example of plasmonic devices with Dirac materials. The Italian-Taiwanese collaboration, with a particular contribution from Qin Lue and his group at the National Cheng Kung University, starts in its activities from the growth of single crystals and their exfoliation in nanosheets by means of liquid phase exfoliation. Materials are usually topological phases of matter or van der Waals semiconductors. Their electronic properties are investigated by means of spin and angle resolved photoemission spectroscopy at Elettrasynchrotron in Trieste. And today we will have a talk by Ivan Obornik, beamline scientist at Elettrasynchrotron. Plasmonic excitation and surface chemical reactivity are investigated by means of high-resolution electron energy loss spectroscopy, HRELS, and core levels are investigated by X-ray photoelectron spectroscopy, also with synchrotron radiation. All experiments are complemented by density functional theory. This platform combines growth characterization, but also application in the field of catalysis and gas sensing, optoelectronics, and plasmonic applications such as plasma wave terahertz photodetectors and thermoplasmonics, also with the implementation of new applications such as photothermal membrane distillation for seawater desalination. Tomorrow we will have a talk on this activity. These are the most recent highlights of this collaboration, and I will start discussing the main features of physicochemical properties of surface of advanced materials, and then I will discuss regarding application in the fields of catalysis, gas sensing, ambient stable optoelectronic devices, and finally plasmonics. The materials which are investigated in this collaboration often display topological electronic states, as for the case of Dirac semimetals. The presence of massless Dirac fermions comes from the presence of linearly dispersing electronic bands. And this has been revealed for the first time for graphene, which is a monolayer of graphite, and for surface states of topological insulators. But both graphene and topological insulators are not particularly suitable for large-scale industrial exploitation, because graphene is just a single layer of graphite. And it is difficult to think to a large-scale industrial application of a single layer of carbon atoms. On the other hand, topological insulators only show surface states in highly crystalline surfaces. So it is very difficult to get industrial application with topological insulators. Accordingly, a three-dimensional analog of graphene will be highly desired, and this is the case of Dirac semimetals, which have been experimentally realized only in 2014 for systems showing high chemical instability, such as sodium-free bismuth. So materials with linearly dispersing electronic states already in the bulk are highly desirable. And three-dimensional Dirac fermions will be naturally robust against in situ surface doping, such as environmental contamination, because of their bulk nature. Moreover, usually these materials display ultra-high mobility of charge carriers and giant values of the magnetoresistance. So they are particularly suitable for application. Currently, the interest from the scientific community is moving from type 1 to type 2 Dirac semimetals with tilted Dirac cone. Platinum ditelluride has type 2 Dirac cone, which is located around 0.7 electron volt below the Fermi level, so it is a good system for infrared application, but not for terahertz photodetectors. Currently, we are engaged in the cast of new materials with topological states around the Fermi level. And this is the case of nickel ditelluride, which has a bulk-derived Dirac cone around the Fermi level. And it is naturally a candidate for terahertz technology. By means of angle-resolved photoemission, we discovered the presence of low-energy type 2 Dirac fermions in nickel ditelluride. And we also demonstrated that surface states in nickel ditelluride have a strong spin polarization, reaching around 50%. So it is a good candidate for spintronics. Nickel ditelluride is also a material showing an outstanding ambient stability. As you can see, the morphology of a nickel ditelluride flake does not change even after 10 days in air, in contrast with the case of black phosphorus, which is completely degraded even after a few hours in air. By combining X-ray photoelectron spectroscopy with low-energy photons with density functional theory, we are also able to follow the chemical reactivity of the system For the case of nickel ditelluride, we discovered that the surface gets an oxide skin which remains subnanometric even after 1 year in air, because the tellurium oxide skin reaches just a passivation layer of 0.8 nanometer. The surface of these materials are also directly exposed to small molecules in vacuum condition in order to understand the main features of their catalytic properties. In particular, for nickel ditelluride, we demonstrated that the surface does not react towards carbon monoxide, so the surface is not affected by the problem of carbon monoxide poisoning, which is commonly affecting each nickel and platinum-derived alloys. So nickel ditelluride and related materials are suitable for catalysis, and combining information from density functional theory, we are able to tailor the catalytic activity, which is also tested by electrocatalytic experiments in hydrogen evolution reaction, so the production of hydrogen, and oxygen evolution reaction. We are also able to put in evidence the real physicochemical mechanism ruling catalysis with these materials. As an example, for platinum tin 4, we discovered that the Tafel slope is very similar to the case of pristine platinum foil, in spite of the replacement of platinum atoms with a cheap tin atoms, with a big advantage for large-scale exploitation because of the reduced cost of the electrode. The main reason of the enhanced electrocatalytic activity of platinum tin 4 comes from the formation of a tin oxide skin revealed by means of X-ray photoelectron spectroscopy. The formation of a metal oxide skin also occurs for the case of metal chalcogenides. In particular, gallium selenide and indium selenide, once exfoliated in nanosheets, display a superior electrocatalytic activity in hydrogen evolution reaction. The formation of this metal oxide van der Waals semiconductor heterostructure is a good platform for gas sensing, as we demonstrated for the case of tin diselenide, which has been also tested for gas sensing for both oxidizing and reducing agents. We've also implemented devices based on topological materials and van der Waals semiconductors. We fabricated the simple microwave receivers, and already in the first implementation, we found that palladium ditelluride has a superior performance compared to similar devices based on black phosphorus and graphene. You can see that the photocurrent is 1 order of magnitude higher than the other materials. And moreover, the stability of these devices is really outstanding. Even after 1 month in air, the photocurrent does not show any noticeable changes. We also implemented the THz photodetector based on topological materials. Very briefly, THz is a narrow window between the microwaves and the infrared, and we have not good detectors or sources of THz light. However, THz is particularly relevant for application. Many organic molecules have THz resonances. THz light can pass through the clothes and detect the presence of hidden metals. and so it is particularly relevant for application for body scanner, for the protection of homeland, so in airports, for biomedical application, and for cultural heritage. We carried out rare earth imaging experiments with novel topological materials, finding that it is possible to detect the presence of a metal nut inside an envelope, which is invisible at naked eye, in just 30 milliseconds with a source of 0.12 terahertz, and similarly for a source of 0.3 terahertz, just 20 milliseconds were sufficient to detect a knife. Finally, we are also interested in plasmonics to find new candidates for plasmonics. Historically, plasmonics has developed with silver, gold, and alkali metals, which display resonances in the ultraviolet. But now we are searching materials with resonances in the infrared, in the visible range of the electromagnetic spectrum, with the highest carrier mobility as possible. We found that platinum ditelluride as a new kind of plasmon modes, three-dimensional Dirac plasmons, which occur in the near infrared with an energy of 0.5 electron volt, with other interband plasmons at 1 and 1.5 electron volt. Moreover, we also discovered that tilted type 2 Dirac semimetals also display a new mode due to the out-of-plane oscillation of the density deviation in electron and hole pockets. And this is a gapless and undamped plasmon, which only exists in these materials. In conclusion, thanks to the collaboration of Italian and Taiwanese partners, we discovered that type 2 Dirac fermions exist in platinum ditelluride and related material, which are transition metal dichalcogenides, hosting spin polarized surface states. So they are good candidates for spintronics. The surfaces of these materials are stable in air with just sub-nanometric oxide skin, even after 1 year in air, and the surface is not affected by carbon monoxide poisoning. So it is a good candidate for catalysis. We found good performances for hydrogen evolution reaction and oxygen evolution reaction. And we also implemented microwave receivers and terahertz photodetectors, finding state-of-the-art performances already in the first implementation. And finally, we explored the plasmonics with novel topological Dirac semimetals, finding the occurrence of a new excitation, in particular three-dimensional Dirac plasmon in the near infrared, which are suitable for applications such as night vision devices. And we also predicted a novel undamped plasmon, which only exists in type 2 Dirac semimetals. So thank you for your attention and enjoy this bilateral meeting. I'm Antonio. Maurizio.
Okay, sorry. Thank you so much. I was saying, Antonio, for this brilliant presentation, which tells us something about a success story of true, real collaboration between Chinese institution in Taiwan and Italian universities. Well, questions? Time for questions or curiosities? Please, Ambassador.
Yeah, just to say the 2 words in congratulatory message for the excellent presentation. So I look forward to seeing all of you in presence, maybe in a Taiwanese restaurant, because we believe that this is a very exciting moment when we initiate. For me, this is the first time I can witness such a successful scientific and technological and academic exchange. So I look forward in mingling with you to learn in person and more closely with you in the future. So because of my agenda, I regret I need to leave the floor, but I wish of you the conference, the very successful one again. So I will be in contact, and I look forward to seeing you very soon in the future also. And also, I just take this opportunity to say hello to my counterpart, my good friend, Minister WGO, for your excellent job in Taiwan. So look forward to seeing you all soon, and have a very nice day.
Thank you, Andrea.
Thank you, Ambassador and Andrea. And
Ambassador, I look forward to come in Rome to the Taiwanese restaurant.
Yes, I wait for you.
Okay.
Okay.
So
if I may also say something.
Disagreement, yeah? We all are witnesses of disagreement. Well done. Well done. Well, some technical question for Antonio?
Professor Perusini, I would like also to say goodbye to Ambassador Lee, and I will also have to take my leave. I will put up a Facebook post on the Italian office website about the event that is taking place. And whenever it would be possible, and this is a question addressed to Professor Politano, if you will have us have maybe a resume of the outcomes, because I will certainly share it with in my contacts here with Ministry of Science, which is present, of course, but also with other Taiwanese institutions, as evidence of the potential that Italy and Taiwan have in this area. So it will have to be something short, but that I can use for in my activity. I believe maybe this would be also useful for Ambassador Lee.
Certainly.
For sure.
Sure.
Arrivederci, a presto.
Grazie. Thank you so much.
Thank you.
Time and good luck for everything.
Grazie ancora a Professor Perusini e Professor Politano e a tutti i partecipanti italiani.
Grazie.
Veramente un piacere, ho imparato molto anche.
Thank you so much for your kindness, for being with us. We appreciated a lot your time and your participation with, let's say, ideas and perspectives to this meeting.
Please do count on my office for any follow-up and for future similar initiatives like this one, which I highly commend. Thank you very much, Professor.
Surely.
Thank you so much.
In contact.
Arrivederci.
Arrivederci. So, Antonio,
can I make a question?
Yes.
Yes.
Do you want to raise a question?
Yeah.
Great.
Thank you, Antonio, for the excellent, impressive presentation. Just a very small question. Concerning the oxygen and the hydrogen evolution reaction, what is the scale-up potential of these materials?
For hydrogen evolution reaction, we have studied mainly the physicochemical mechanism ruling the catalysis. We find that, for example, platinum tin 4 has a very good potential for technology transfer, and thanks to the capability of the group of Professor Chin-Shan Lue, I believe that there are all possibilities to a large-scale industrial exploitation, because already in the first implementation, the performance for hydrogen production, so hydrogen emulsion reaction is already competitive with platinum foil, with cost reduced by 70%. So the direction is that.
That's
Thank
clear.
you. Grazie, Antonio.
Is any other questions?
Yeah, I have.
Yes, please, Alessandro. Nice to see you.
Ciao to everybody. See you. It's a pleasure. So, Antonio, I have a technical question just to wrap up actually and go quickly. So, about the biosemi method that you mentioned in the type 2 form. So, what do you think actually is the temperature range of operation? So, are they operated at low temperature, or they can be available at room temperature?
In all our experiments, we use room temperature. One of the main advantages of direct semimetals that we have exploited as an example for terahertz photodetectors and is just that topological states exist at room temperature. And another advantage is that we do not use any capping layer, so any encapsulation strategy is required. And this is a big advantage for nanofabrication with the possibility of large-scale industrial exploitation.
And do you think that the topological character still remains at low thickness, so just to have a thin film with the topological characters in the biosemi metal form?
No, we are investigating bulk form because for direct semimetals the topological states come from the bulk, because bulk valence and conduction band of the bulk form linearly dispersing bands. Moreover, this system also displays topological surface states with spin polarization. Concerning the exfoliation in nanosheets, one important issue is that the topological states only emerge for 3-4 layers. So the single layer is actually not a topological material. It is definitely a semiconductor, a trivial semiconductor.
Or at least or a metal if it is in a 1T prime form. Yeah, but this is exactly what I wanted to know actually, because it's so you need to actually increase the thickness to
Yes.
to impart some topological character. And I would be pleased actually to know that the Taiwanese guys actually would be interested in this kind of materials for establishing collaborations, something like that.
I'm sure that Taiwanese speakers of this workshop are expert in growth and synthesis. So also the expertise is complementary to yours, because you are an expert of epitaxial growth, while as an example the next speaker, Jin-Shan Liu, is an expert of the growth of bulk crystals. So I think that we can move in a joint direction with Jin-Shan and you.
Thank you.
Thank you, Alessandro, for this question, and thank you, Antonio, for your answer. I think that we are in time for going ahead with the presentations. Let's thank Antonio, and let's move to the next speaker, who has been already mentioned. There is Professor Jin-Shan Liu from the National Cheng Kung University.
One of the chairmen of the bilateral workshop.
Okay, that's important as well. And he will talk about the Italy-Taiwan cooperation on advanced materials, and we will speak about the contribution from the National Cheng Kung University, indeed. Please, Professor Liu.
Yes. Can you see my screen?
Please. We can see.
Yes.
Okay.
Your presentation.
Okay. Okay. Thank you.
You can go to the presentation mode.
Okay. Good morning, Italian friends, and good afternoon, Taiwan. In this presentation, I will share my experience with the cooperation between Taiwan and Italy on our single crystals. Dr. Jianong Guo is the key person who grew these crystals. And my name is Qinshan Lu. I teach in Physics Department of National Cheng Kung University. And I recently joined the program on key materials in Academy of Innovative Semiconductor. I'm also a member of TCECM. This was supported by Ministry of Science and Technology, MOST. First, allow me to briefly introduce to National Cheng Kung University. Okay, like this, the map of Taiwan, and the National Cheng Kung University is a public research university located in Tainan. Tainan means southern Taiwan, and the capital Taipei means the northern Taiwan. And this university was founded in 1931. It was 90 years old, and last month there was a 90 years anniversary. And the Physics Department of NCKU was founded in 1956. It's 65 years old, and this is a big banyan tree in one of the campus. It's so big, so beautiful, and it became a logo of an insurance company. The Crystal Growth Lab was established in 2012, about 9 years ago. We have 10 furnaces of different kinds, including box furnaces, vertical furnaces, tube furnaces, and two-zone furnaces. And this is the photo picture of Dr. Guo Jianong. Jianong used 3 different methods to grow the single crystals. The first one is the flash growth method, and here I show 9 representative pictures of the crystals. Each individual has its own interesting physical properties. For example, MBTE4, this is a needle-like crystal, is a one-dimensional charge density wave material. And CUTE is a novel CDW material. PTTE2 is a deluxe semi-metal. PDSE2 is a 2D semi-metal. And these 2 are superconductors. The second one is called the CVT growth method. Jianong already grew many 2D materials using this way. And for this one, MBP is a wire semi-metal with a very high fast mobility of the carriers. And this one, CRPS4, MMPS3, MMPSE3, they are van der Waals materials with anti-ferromagnetic ordering. And these are materials, so-called ferroelectric materials. The third one is called the Bridgman growth method. And for example, tin arsenide is an important superconductor, and tin selenide is an important thermoelectric material. These materials has a very low thermal conductivity. In the very beginning, we focused on so-called 3-4-13 systems. These materials show very important interplay between lattice distortion and superconducting ground states and or magnetic ground states. Up to now, we already published more than 10 papers based on these materials, and most papers are published on Physical Review B. About 5 years ago, Jianong grew start to grow transition metal dichalcogenide. Okay, Jianong can grow the very large and high quality TND materials. And each material, each material shows very sharp spots from the Raoult diffraction patterns. It confirms the good crystallization of these crystals. For TMD materials, in addition to their topological surface states, each shows interesting physics properties. For example, PDT2 is a superconductor. PDSE2, PTS2 are 2D semiconductors. And the VSE2 is a CDW material with transition temperature of about 110 K. Okay. About 5 years ago, we started to cooperate with Professor Politano of University of L'Aquila. Okay. We quickly have published 2 papers on top journals based on PTTE2. This one was published on Physical Review Letters. Physical Review Letters is the best journal in physics. Up to now, this article has been cited by 50 times. Another was published on Advanced Functional Materials. This is a high-impact journal in material science. So this article has been cited by 40 times now. We then extended the cooperation with more Italian groups. So these institutes are scattered all over the country of Italy, from North Milano to South Calabria. So these are very, we have very wide cooperation with the Italian institutes. So our cooperation involves very rich research topics. So these are papers related to the optoelectronics. They are published only within 3 years. These results demonstrate these crystals can be used to fabricate terahertz antenna and terahertz detectors. So our crystals can also be applied to the field of catalysis. So these are the presented papers about the issue of the catalysis published in within 2 years. Okay. So those crystals correspond to the materials for the catalysis application. So these are papers related to the issues of gas sensing, and so these are papers related to the issues about plasmonics. These are the presented papers that relate to the issue of about the science, surface science, and the topological physics. So overall, we have delivered more than 20 papers in 3 years. Most were published on top journals like Physical Review Letters, Nature Communications, Science Advances, and the ASCS Narrow. Recently, Jianong grew a variety of 2D semiconductors. For the transition metal based compounds, people are more interested in their magnetic properties because they belong to the so-called 2D van der Waals ferromagnets. In addition to their important properties in magnetism, I think I propose to study the possible applications on photoelectronics because of their semiconducting behavior. For example, these materials are direct band gap semiconductors, and they should be good candidates for application in light emitters and lasers. Okay, and for this one, one shows the ferroelectric ordering above room temperature, and would be a good candidate for ferroelectric applications. So finally, I think the great contribution from Professor Politano on the promotion of the cooperation between Italy and Taiwan, and I expect to see a more extensive cooperation between these two countries after this symposium. And finally, I think that I need support from NCKU, TCECM, and MOST. Okay, I think I start here. Thank you.
Ogni volta le rozzine accende.
Thank you so much, Professor Qinshan Lue, for your presentation and for the let's say the collection of beautiful examples of great materials that are being grown in your laboratory, and the many publications that are resulted from them. If there are questions or comments or suggestions for possible collaborations, please, they are welcome.
I have just a question regarding the possibility to a large scale production of platinum tin 4 as an example. If we identify a material which could be suitable for hydrogen production as an example, the need of a large quantity supply to industries will be challenging. Can you comment on it?
And Antonio, I don't quite understand
I'm asking if it is possible to produce a large quantity of platinum tin 4 or similar materials for industrial application to increase the quantity of crystals.
We will try. We will try. It might be possible. Yeah, we will try. Yeah.
To go from grams to kilograms. I think that it will be demanding. This is the goal.
There will be different techniques and.
Do you think that it is the scalability? Do you think that it is feasible?
Yeah, it's possible. Yeah.
Okay. If there are no any other question, let's thank Professor Qinshan Lue. Thank you so much for your presentation, for staying with us. And by the way, I've seen that you have a collaboration with my institute, ICCOM in Florence. I'm very happy of that.
Yes,
reaction, I guess. Yeah.
Andrea Marchionni, Francesco
Marchionni, and the people of Francesco Vizza as well. Quite good. Well, let's move then to the next speaker. She came from CNR, the Institute Officina dei Materiali in Trieste, and there is a double affiliation with Elettra Synchrotron, also in Trieste. The speaker is, I guess, Dr. Ivana Vobornik from Croatian in origin, and she's currently working in Trieste, I guess. Please, Ivana, you will present your lecture about direct insight into the electronic band structure and spin properties of novel topological materials. Please, go ahead. And try to stay for 20 minutes. We are a little bit in.
Yes, I will try to do my best. Good morning and good afternoon to all colleagues. It's a great pleasure to participate in this.
Can you move to the full screen presentation?
I guess I did so, but let's then try to. Just one more.
Otherwise, okay, anyway.
You are not seeing the full screen?
We see your comments.
You're the one with the notes. Okay, okay, let's get out of this. Just 1 second.
And then
From
down.
slide and show. Okay.
Yes, yes, yes.
Okay.
I did that, but I don't know why you are. Okay, let's do one thing. I do this.
Just a few seconds, I guess. Okay. No.
Is it now better?
Yes, yes, okay.
Okay, excellent. Thank you. So then again, good morning and good afternoon to all colleagues, all collaborators, all participants to this workshop. It's a great pleasure to take part in this initiative, and I would like to thank the organizers for inviting me to participate in this workshop. Thank you, Chairman, that you pronounced nicely my name. Yes, indeed, it's not Ivana, it's Ivana. I'm Ivana Balbarnik. I'm a scientist at the National Research Council of Italy in the Istituto Officina dei Materiali, that is here in Trieste, in Italy. So our previous Professor Lu previously showed the map. So we are at the very north of Italy. You can see here also the very north part of Mediterranean, where Trieste is placed. But Trieste is also having the image of a scientific city, so a number of important campuses and a number of important facilities are placed in Trieste. You see my affiliation is CNR-IOM, but in fact IOM is also managing a number of beamlines at Elettra Synchrotron, so I'm beamline scientist at one of them, at APE beamline. This kind of little vehicle here in Italian is called APE. So you will be, this is a sort of a symbol of our beamline, but APE is also operating not only within Elettra facility, but also within NFFA Trieste facility, which I think can be also quite appealing for future collaboration with Taiwanese partners. The outline of my talk is the following. Is already introduced by a previous speaker, and in fact, our recent collaborator. I will be speaking about novel topological materials. These are typically two-dimensional materials where strong spin-orbit interaction induces spin momentum locking. And they are also hosting the first solid materials that are hosting relativistic quasi-particles, such as Dirac, Weil, Majorana fermions, and so on. Our collaboration, in fact, we were involved in collaboration through Professor Politano. We got involved in 2019, and from that moment on, we published 6 papers, and it's important to say also that we are working in a difficult time of pandemic restrictions. 4 of these papers in very high impact journals. So we have 1 Nature Communication, 2 Advanced Functional Materials, 1 ACS Nanos, as already listed also by the previous speaker. And the case study that I will be mentioning here are related to these 3 materials: nickel ditelluride, nickel tellurium selenide, and platinum 3 tellurium 4. In all this, the facilities that are here based in Trieste were strongly involved, mainly by angle resolved photo emission with also spin resolution, but I will also briefly introduce other possibilities that are available here for eventual future collaborations. Among the collaborators, of course, these are our Taiwanese partners. We have Antonio at Aquila. We are here at Trieste, and of course, important partner is also Indian partner who supported us with theoretical calculations. Let me introduce my laboratory. APE beamline, we say beamline, but in fact these are 2 beamlines. This is unique such configuration at Elettra Synchrotron. These are 2 canted beamlines. They can operate contemporarily, and we make this division between low energy and high energy based on the photon energy range that we cover. Low energy branch is dedicated to high resolution angle resolved photo emission with spin resolution from recently, And at high energy, it's possible to do XPS, XAS, XMCD, XMLD spectroscopies, and from recently also the spectroscopy in Apparando and at ambient pressure. But the core of our business is basically here, which is zoomed on the right-hand side of my slide. We indeed have two powerful spectrometers that receive radiation from Elettra, but as you see, they are connected in situ, and we have a number of offline facilities to prepare or to characterize our samples. We have also the growth possibility, so we can grow our own samples by in situ pulse laser deposition. We have STM, which is operating with atomic resolution, and then any sample can travel between all of these possible facilities here that are operating within NFFA Trieste. The core of our business, especially on the ARPES side, is the spin resolution. Spin resolution is crucial for the kind of materials that we are studying nowadays. Our spin detector is called VESPA, which stands for Very Efficient Spin Polarization Analysis. The scheme is here. We can analyze the photoemitted electrons in terms of their energy and momentum. And get the energy dispersion, and then we can also get it in a spin resolved mode, and these are an examples of spin polarized states in two different systems. Our experimental chamber was, in fact, in the time that we introduced the spin detectors, also presented in the Journal of Synchrotron Radiation, and this is the scheme of how it looks like, and I hope that our colleagues, also through the programs of exchange that were introduced today, will be able to come and to see how and where we are working. So topological materials, let's introduce briefly. Some words were already spent on those. These are typically two-dimensional materials. So if you speak about two-dimensional materials, the easiest two-dimensional case is a surface of a metal. On a surface of a metal, you can often find the surface states, which basically behave like free electron states on the surfaces. Their dispersion is parabolic, like this. But then if you introduce spin-orbit coupling in heavy metals, for instance, like gold, Rashba interaction will split this parabola, free electron parabola, in two, each for a certain spin direction. If spin-orbit interaction increases further, the two parabola are further shifted, and you end up with a sort of a linear dispersion, and each branch of this dispersion is of certain spin polarization. So this is what we speak about when we speak about Dirac electrons and spin momentum locking, for instance, in topological insulators. Relevant quantities here are, as you see, electron, momentum, and spin. And the only technique that allows the direct access to all of them is spin and angle resolved photoemission. This is, of course, based on the photoelectric effect. The outgoing electrons, when photoexcited, are bringing the information about their energy, about their momentum, and about their spin inside the material. And then, indeed, it was possible to measure the spin polarized states, surface states of gold when commissioning our instrument, when we're commissioning VESPA, but also we did the work on topological insulators that were grown in our PLD system. So this is bismuth selenide, famous topological insulator with two spin polarized branches of the Dirac cone. As I said, topological materials are hosting relativistic quasi-particles such as Dirac, Weil, Majorana, and then now there is all new classification of materials like Dirac semi-metals of type 1, of type 2, Weil semi-metals, type 1, type 2. In our talk, I will stick to Dirac ones. So we will be looking either, I would say, straight or tilted Dirac cones, and we will try to see how they can exploit it in applications. Fortunately, some of these applicative aspects were already handled by Antonio in his previous talk. Transition metal dichalcogenides, as the name said, these are materials formed by transition metals surrounded by chalcogenide atoms, such as sulfur, selenium, or tellurium. They are layered materials. They have a strong intralayer covalent bonding and weak van der Waals interlayer coupling, which allows them then to be exfoliated similarly to graphene, and depending on the filling of the transition metal d electrons, their ground state can be either semi-metallic, metallic, semiconducting, or superconducting even. And despite the fact that we always push for their two-dimensional properties, properties are in any case conditioned by the number of layers. So for instance, famous example is molybdenum disulfide, which is indirect band semiconductor, but becomes direct gap semiconductor in a monolayer form. Independent on that, many of them host very strong spin-orbit interaction, and this spin-orbit interaction in one way or another produces strongly spin-polarized states. And therefore, they are very suitable and very much investigated candidate materials for future spintronic applications. So yes, this is what I basically said. They are in fact also candidate materials for this kind of architectures of two-dimensional van der Waals heterostructures. But in order to implement them into future devices, it's important to get knowledge and control of their electronic and spin properties. So in our work, in our collaboration, we in particular concentrated on group 10 transition metal dechalcogenides, where for the first time type 2 Dirac fermions were spotted. So type 2 means that this Dirac cone is not anymore along the energy axis, but it's tilted due to Lorentz violation. And what this implicates is that the Fermi surface is then formed by open electron and hole pockets. And this can result in phenomena such as magnetoresistive effect, where the material conducts electricity only for a certain alignment of electric and magnetic fields. Our collaborators and colleagues from the UK were the pioneers who investigated palladium and platinum-based dechalcogenides, and in fact, they, with very careful analysis, understood that the chalcogen p electrons, through interplay between crystal field splitting, spin-orbit interaction, and bonding anti-bonding splitting, result both in the bulk Dirac states and in the topological, in a numerous topological surface states, which they call the ladders in this material. But the point for both platinum and palladium base materials, this bulk Dirac point, which we were mentioning, is quite low in the occupied states. So it's not suitable for the real applications of these materials. Typically in topological physics, the heavier is the better. So maybe for this reason, nickel counterpart, which is the lightest here, was neglected, but there was a recent, not anymore recent, so recent work that was predicting that the bulk Dirac point in nickel ditelluride would be very close to the Fermi energy. So this is the material that our Taiwanese colleagues produced, and we studied the electronic properties and indeed found that bulk Dirac point is very close to the Fermi energy, slightly above the Fermi energy though in this particular case. But besides that, this material was also found to host a number of spin polarized states, both deep at higher binding energies, but also very close to the Fermi energy. And in fact, the proximity of the spin polarized surface states to the Fermi energy was successfully implemented in the realization of high frequency rectifiers. We then move to a similar compound. So here, some tellurium it was substituted with selenium. So this is nickel tellurium selenide. And indeed, this small play, I would say, with the structure or with the constituent atoms, allowed us to bring the Dirac point below the Fermi energy. Now, the Dirac point in this particular case is at 250 milli-electron volt below the Fermi energy. And in fact, I'm not showing you here, also in this particular case, there are a number of spin polarized surface states. But what was interesting, the fact that this tilted Dirac cone was below the Fermi energy, is that it was possible to implement this material in a microwave receiver, which was earlier also presented by Antonio. What remains of my time, I will just dedicate to present the facility that we have in Trieste, which is NFFA Trieste. This is a facility, meaning open to anyone, open to scientists worldwide. They can, of course, check our website, they can check our catalog and decide the experiment they would like to do and apply for doing their experiments. Just a little bit of hint of what kind of approach, of what is the advantage of the approach that we can offer. This is an example of the study that we did on platinum-3 tellurium-4. This is not dichalcogenide, but the structure is a little bit more complicated. We have alternating layers of platinum ditelluride and platinum-2 tellurium-2. And with the three sets of techniques here, we were able to identify different surface termination that this material can offer. So it can terminate either at platinum-2 tellurium-2 or platinum-tellurium-2, as seen by scanning tunneling microscopy, and seen also by XPS. Further, we extended the study also to angles of photoemission. Both of these terminations are hosting, in fact, distinguishable electronic states, which then we could link to the determined termination, but also both of them are hosting different spin polarized states. And in fact, this kind of configuration of different spin polarized states at the surface of the same material is quite appealing for spintronics applications. So I hope that with this, I gave you a hint of a case studies of the materials that we've studied so far in collaboration with Taiwanese counterparts. And I also am inviting you to join us in Trieste. Hopefully times will be better and we will be able to extend our collaboration in person. I'm now not mentioning here, but there are many new materials that we plan to investigate in the framework of this collaboration, and I hope that we will be able to present in future new results regarding the continuation of this collaboration. Thank you very much for your attention.
Thank you, Ivana, for your very exciting presentations, very complete, very exhaustive. And I hope that you have raised curiosities in people on the other part of the screen. And so time is for questions. Please, curiosities as well, or technical questions are welcome. Let's see, somebody will present some, will raise his hands.
I have a curiosity on the feasibility of spintronics with these materials. Can you comment on it?
Of course I can. We have wonderful collaborators such as Antonio, who is taking care, in fact, of these applicative aspects, because I myself am doing fundamental research, basically dealing with electronic band structures and spin structures. So once we identify the candidates, it's very important to have a collaborator who is able to pick up the candidate material and try to build a real device. And this, I think, is a very big advantage of the collaboration that we are currently having, because the applicative aspect is often not treated adequately, because these are new materials and, of course, quite challenging. So one has to really invest the time and the vision as well in exploring their properties. So I think in this collaboration, this is being done quite successfully, and I hope we will continue in the same direction. Hopefully also with Taiwanese food and maybe Italian wine put together.
Surely. I'm not sure about Taiwanese wine, but for Taiwanese food, I can confirm that it's really an excellent Chinese cuisine. Very peculiar and very good. So I agree.
I agree.
Okay, thanks. So
thank you.
Just another question or curiosity, let's say more curiosity than question. Many years ago, as I was young, I was working in homogeneous chemistry, and I published 3 or 4 papers describing metal complexes containing nickel, palladium, and rhodium, containing ditellurium unit as a ligand. I mean, complex in which, for example, 2 nickel atoms are sandwiched by a ditellurium unit, nickel, tellurium, tellurium, nickel, forming a sort of microclusters stabilized by additional phosphine ligands on the 2 metals. So I am wondering if this kind of, let's say, molecular materials could be used as precursor to synthesize, let's say, nickel ditelluride, for example, rhodium ditelluride, or similar compounds. Do you have idea that this kind of molecular compounds have been ever used for approaching this synthetic chemistry?
Well, from my point of view, intuitively, I could say yes. I think this would be more of a question for Professor Liu and collaborators who are really doing the growth and the synthesis of materials. I typically, you know, when we are interested in a material, we express our wish list, and then a good grower picks up the wish list and produces the material. Yes,
that's correct.
But as I said, we are also having, okay, I haven't introduced much maybe in this particular case, but we have in situ pulse laser deposition. So I guess in view of the pulse laser growth, it could be possible also to discuss the issue maybe a little bit in more detail. Certainly, we can do it also after the completion of the workshop.
Yeah. Okay, thank you, Ivan. It was just a curiosity. Other questions?
I have a sort of like a general question. So, well, actually, Taiwan is developing some laser RPS and time-resolved RPS. I think Professor Zhiwei Luo is in charge of that development. So I wonder if there's some collaboration between your institute and, say, the Synchrotron Radiation Research Center in Taiwan.
In fact, at the moment, not yet. I was taking carefully notes from the presentation of Stefano Pelagi earlier. I think this kind of collaboration and exchange of students and scientists as well would be crucial to deepen our knowledge. I think we could profit immensely, both counterparts, from this kind of exchange. So I'm in fact looking forward to strengthen this kind of this aspect, particular aspect of collaboration. We are always in search of young and talented students or postdocs who could join this research and also be trained in the techniques that we can offer here, bring their knowledge back to their home laboratories, and bring also to us the knowledge that they have from the training at their home laboratories. So that is an excellent aspect of the collaboration, which I hope will be further extended in near future. So we will definitely keep in touch, and I think
so I think one of the important result of this meeting is mission of this meeting is Antonio and Chin-san need to like list give us a list of the expertise on both sides, and maybe you can do some matchmaking, and it'll be wonderful.
Exactly.
Thank you. That's
exactly.
a quite good idea.
Yes.
Okay. Is there any other question for Ivana?
No.
If not, we thank Dr. Vobornik, Ivana, and we move to the next speaker. Thank you, Ivana.
Thank you.
The next speaker is Professor Alfredo Davide Ferella. He comes from the University of L'Aquila, from the Department of Physical and Chemical Science, but at the same time is, let's say, working also at the Gran Sasso National Laboratory one of the most important, let's say, center for nuclear physics in Italy, and I would like to say in Europe, at least. And we are a little bit in delay, but you have all the time that you need. That is about 20 minutes for your presentation, including some questions. Please, Professor Ferella.
Thank you very much, Pierre, for the nice introduction. And thanks. I would like to thank Antonio and Carlo for giving me the possibility to present you some exotic topic. But I think since you are looking for applications to
Alfredo, may you speak a little bit loudly, please?
Yes, I'm trying to. Is it better now?
A little bit.
Yeah, okay. So I will try to shout.
Yeah, thanks.
Okay. So yeah, I'm trying. So we in our field, which is more fundamental physics research, we still have the need to find some new materials for the detection of dark matter. And so I, together with my colleagues that I've listed here, have started some work still at Stockholm University, but I still keep my involvement or interest in this kind of researches, and I will try to done so far. So yeah, so here is the content of my presentation. I will give introduction. Most of you are from the field of dark matter, so I need to. This is important for motivation. Then I will tell you how we detect the dark matter. I will tell you how dark matter detection. So as an introduction, I need to convince you that dark matter exists in the universe, in the sense that we see it in its impact in at different scales from the galactic scale. See my mouse, right? And so you when you base your observation on the rotation speed of stars in the galaxies and also on gas in the interstellar medium as a function of the position within the galaxy. If you use only the luminous matter from the galaxy, then you expect an exponentially falling type of behavior. However, what we see is instead observations is a flat rotational curve, and this is an indication that there is some other matter that we don't account for with that curve that sits there and then it produces in the galaxy a halo. Then we have also other type of observations at different scales. When we put together all the information, then we get a picture that tells us that only 5% of the matter in the universe is ordinary matter, mainly what we have been discussing so far in this symposium. The rest is something that is called dark matter, and something that is even more obscure, that is called dark energy. So now I don't think I need to convince you that dark matter exists. But it's still it's a puzzle that remains because we know that dark matter is matter. It leads to the formation of structure and galaxies in our universe, and this comes from observations, from current observations, and also from cosmic microwave background observations of the small fluctuation in the temperature, and also we know that we have a model that is called the cold dark matter model that gives us some precision measurement or precision predictions on the composition of the universe and on dark matter existence. However, what we measure escapes our understanding, and because we know that there is 81% of matter in the universe that is of unknown nature. So we want to understand what is the nature of this dark matter. So let's recap what we know about dark matter or what we don't know. So what we can exclude, it cannot be. So as we said, it exists, and if we want to, if we look at the structure formation, so at the large scale structure, so-called, in the universe, in the current universe, then this dark matter has to exist since the early universe. We have constraints from astrophysics and for searches for new particles. So what we know that it is the particle, the dark matter particle has to be massive because it has some gravitational interaction. It is long-lived because it comes from the Big Bang, and in the Big Bang it was already there. It is electrically neutral, otherwise we would have electromagnetic interaction. It is non-baryonic. When we talk about baryons in our field, are mainly nucleons, neutrons, and protons, which make the mass of our atoms, or makes the vast majority of the mass in our atoms. It has to be collisionless, and it has to be cold, that is non-relativistic. None of the standard model particles, so the standard particles that we know, can make this dark matter. So we look for something that goes beyond our standard model. There are many theories. There's a plethora of particles that have been predicted by our colleagues, our theory colleagues, that span over this large parameter space of interaction probability, interaction cross-section versus mass of the dark matter particle. What the community has focused so far is this small green region, which is called the WIMP, which is weakly interacting massive particles, and more recently the community is moving towards lighter dark matter particles, so in the region between the kilo electron volts to loads over c squared mass. So just to give you an idea why we have believed so far that the WIMP paradigm is the right one, is that if you look at the universe as it is, so if you look at the evolution of particles in the universe, so let's say the number density as a function of the temperature of the universe. So temperature is, of course, means energy, and so when the universe in the early universe, the energy was very high, so particles would annihilate with each other and be in thermal equilibrium. So dark matter particles would annihilate into standard model particles, and standard model particles would annihilate into dark matter particles. At some point, when the temperature was below the rest mass energy of the dark matter, then the standard model particles wouldn't have enough energy to generate dark matter particles. But so in this so a suppression of the dark matter particle production until a time that is still valid today, when the standard model particles also don't have enough, cannot meet because the universe is expanding, so that the standard model particles wouldn't interact so easily with each other because they are kind of far away, and so we are left with a number density, so a density of these particles up to today. And this, if we plug in what we observe from, for example, cosmic microwave background as the density of this dark matter particle, then we end up in with a, let's say, a cross section, okay, that is in the same order of the weak scale. And magically, and this is what is what is called a WIMP miracle. Magically, also from supersymmetry, we also have a prediction of a standard model, of a non-standard model particle that is called the neutralino, that has a very, very similar properties. So somehow there are something. So we don't believe that it was just a coincidence that these two things come together, somehow predicting the same type of particle. And so far we have been looking for WIMPs. However, now the WIMP is kind of escaping our detection, and we are really getting into a region where the WIMP paradigm is not so well motivated. So we are going towards lighter dark matter particles, and this lighter, so it is, can ask ourselves, is there some kind of new force? But what is the connection between the, let's say, dark matter and the new force? Well, the answer is that dark matter is neutral would be neutral under the standard model forces, but it's charged under a new so-called hidden force, which is hidden in the sense that we don't see it, and because of some paradigm. So now the question is, can we see it experimentally? Well, of course, it's a good question. We don't know exactly, but based on good symmetry arguments and also on cosmological motivations, given the dark matter abundance, we think that there might be some so-called portal interaction between the hidden sector dark matter and the standard model particles, and so we look for dark matter detection. How do we look for dark matter detection? We are immersed in a halo, as we said before, and these are also the dark matter. Sorry, these are stellar angular circular velocity of stars within our galaxy. So we see that there is a shift between what we expect from luminous matter and what we observe, and so we know that there is a dark matter halo also in our galaxy. In this dark matter halo, the dark matter particles have a certain Maxwellian distribution. Also, the sun is moving around the sun with a certain velocity, and the Earth is moving around the sun. Sorry, the sun is moving around the center of the galaxy, and the Earth is moving around the sun. And so, by looking at this mutual exploiting this mutual movement, we expect that dark matter particles have some speed coming against our detector, so that we can see their scattering on our detector materials. And also the fact that the Earth is moving around the sun gives us also a so-called annual flux modulation, which is a 3% effect, but there is also another effect that is a diurnal modulation in direction that is a larger effect of about 30%. And in this sense, well, I don't know if we have time to discuss this, but the direct material would be a very good material for looking for this directional preference. So the current status is this what is shown here. We have the cross section of the WIMP particle as a function of the mass of the WIMP, but we are, as I said, we are going with towards lower threshold towards lower mass WIMPs, and so if you look at the kinematic of the process, so you see that the kinetic energy of a particle is if the particle has GeV or above GeV scale, then the kinetic energy is in the order of keV. But if the lower we go with the mass, the lower the energy is going to be, the kinetic energy is going to be, and also the lower the momentum transfer. So at some point, the current WIMP paradigm predicts the interaction of WIMPs with the nuclei, but once we go to lower masses, the particle to which the dark matter will interact are the electrons, and so we have to take into account all the electronic structure of our system, of our detector, and we need sub-electron volt thresholds. So far we have been looking at this range of mass, but we are going towards this mass range, so between keV and GeV over square mass, and here you see the type of energy that we are looking for. And so, well, this meme is an interesting way of the mood within a particle physics field, so in which any material could be a good candidate for dark matter detection. So just to tell you that there have been already, because it's a challenge to go to such low energy, to be at such low energy deposits, but there have been already reported the detection of single electrons escaping or passing from band to band in some solid state detectors. So we believe that this is a possibility, and so we proposed the Dirac materials for dark matter detection, and here you see that this is the recoil spectrum. So here you see that the recoil spectrum as a function of the Fermi velocity. Of course, the interaction of dark matter would be kinematically forbidden if the velocity of the dark matter particle is lower than the Fermi velocity. So you see, and this is something that is also expressed here in this spectrum. This is somehow the spectrum, the interaction, the spectrum that you would see in your vector as a function of the Fermi velocity, of course, considering some fixed sector. And so you see that the main, the most important, or one of the most important parameters here in this search is what is written here as delta, is the band gap. So with the band gap, with the lower the band gap, the higher, let's say, the sensitivity. Here is reported the cross section as a function of the mass. And you see that already TDLS, I think, has a 10 milli-electron volt threshold, and this one has 25, I guess. So you see that with the lowering the threshold, you increase your sensitivity, both to lower masses, but also to lower cross sections. And so, well, I don't know if I need to go so much into the details of the interaction of dark matter, but we have two types of interaction. Can be direct scattering, but can also be a so-called kinematic mixing, in which the dark matter particle is absorbed within your material, it produces a photon, and this photon then makes an electron in the valence band to jump into the conduction band. And this is the reason why also the optical properties of the materials are important. And you can see that in this plot, the interaction cross section as a function of the WIMP of the dark matter mass is reported compared to conductor, for example, and also to semiconductors. And so you see that the Dirac material is very good potentials. So what we want, since we want to detect small energy deposits, we want, if possible, to have some directional sensitivity. If possible, our materials have some magnetic properties and interactions, but it's not good applications that we're discussing right now. So the boundary condition for a material that is suitable for our detector is it has to be affordable in the sense that it has to realize, to grow. It has to have chemical properties, good chemical properties. Also, well, we need to look at the readout, how the way to read out the single or few electrons that are excited to the from the valence to the conduction band. So what we have done is this kind of exercise. So we have put together somehow the expertise from different fields, from dark matter and also solid state theories that have a big so have a big database of Dirac materials, especially. We have looked at the organic Dirac materials, but of course this is extended because to this. So we have put together dark matter or particle physics, material science, and also data science, because what we have a big set. Have a big set of materials. Back then, when we did this publication, was 7,000 stored in the database. Yesterday I checked, and now they are at 40,000 materials. So what we do is an advanced data mining by querying the database for specific requirements. The requirements are that we first look at the band gap, and the band gap has to be as low as possible, as we said. So we narrowed this gap, and we identified 220 materials. Then we require that this material is magnetic. So we didn't want to have magnetic moments, and so we came out with somehow the selection restricted to these materials, and then we that have a band gap in the order of 40 milli-electron volts, and so we have also investigated the band structure of this material that has also another advantage, that when you turn on the spin orbit coupling, this material, I mean a small gap opens around the Dirac cone, and this is extremely good for us because we don't want the spontaneous transition of electrons from valence to conduction band. So the existence of a band is of importance for us. So don't know if I took. I guess I took most of the time here, but I hope I gave you an idea of what our needs are and what our idea is to exploit the Dirac materials. I was saying that Dirac material is also directional sensitivity. Antonio has explained before that the Dirac cone in some materials is also tilted. This tilting of the Dirac cone would be a perfect property to exploit if we want to, for example, look for directional the interaction of the dark matter. So knowing the direction of the cone, so we would make like a day-night modulation analysis and see which is the most there is any signature for this day-night modulation, and this would be a clear signature of existing dark matter. So, of course, we could use machine learning also to train our machine with the database, and then we can probably ask the machine to come up with some possible materials that maybe are synthesized yet, but this is a heuristic approach, but it's still something that. So I think I don't need to. Thank you for listening.
Thank you, Alfredo, for your presentation that put us in a very, let's say, for us, I think for most of the people, exotic area. But at the very end, it's important that just real material is necessary to detect and to get the final confirmation of dark material. Well, so the argument is really exciting, and maybe that it raises the curiosity of some people in the audience. And so I raise questions or comments or curiosities. I have just, let's say, comments, a curiosity.
Carlo, you can do.
Okay.
We would like to provide a question.
Yes.
Please.
Do you hear me? Okay.
Introduce yourself, Carlo. Okay, Carlo Rizza.
Okay, Carlo. Yes. From Università of l'Aquila. Okay. Now, Mike, I understand. Thank you. First of all, thank you for your nice talk, Alfredo. I understand that you focus on organic material. It's right?
Yes.
Why do you choose these materials?
There is no.
They are better than. Okay.
No, I don't think there is a specific reason why we. It's just that our colleague at Nordita, they maintain this organic material database that are all Dirac materials. So they maintain this database. So we only use their database to test, let's say, our method or our approach, which doesn't mean that it has to be only organic material. We only identified 2 or 3 materials that are interesting for our applications, but from the organic materials, of course, there are also many other Dirac materials that we know they are not organic, and they still may have exactly the right properties. So there was no specific reason rather than the fact that we already had this. And
okay. Thank you for your reply.
Okay. Is there any other question or curiosity?
No, that's good.
Not, we can just say stop the first morning session. I would like to thank the distinguished guest that opened the meeting, the institutional guest, and then the technical scientists that provide interesting lectures about different aspects which arise a strong importance of cooperation between Italy and Taiwanese institutions. It's time now for the virtual coffee break. We have a little bit in delay, but I guess that 10 minutes break is necessary. And so I convene all the people here in 10 minutes, more or less. That is 11:30. time in Italy, and the corresponding time in Taiwan, that is 18:30 p.m., or probably, if I'm right. And so let's thank all the speakers of this morning session. Thank you so much.
Maurizio, thank you very much for.
It's been a pleasure. Very interesting talks. Very interesting. Just to enter in a world that is not very familiar for Italian scientists, that of Taiwanese universities. I think there is a lot of points that can be developed, a lot of common interest, and let's say I would like just to talk with you in a separate time about CNR and how CNR can better improve the relationships with Taiwan. That would be important as well. So let's go to take this virtual coffee, not virtual coffee, and we'll convene here in 10 minutes more or less. Carlo Rizza will be the next chair person of the session.
Yes.
Thank you, Carlo.
Thank you very much, Maurizio. It is a very big pleasure for us.
No, it's a pleasure for me. I will phone you later. Ciao, Antonio.
Ciao.
Ciao, ciao.
Now we will broadcast some promotional videos on Taiwan during this coffee break.
Antonio, this is Gianluca. Hi, ciao. Can you hear me? I can't hear you.
Gianluca, io ti sento perfettamente, non so se ti sente anche Antonio.
Ciao Gianluca.
Sì, ti sentiamo. Adesso,
Antonio, mi sai dire se sono il prossimo speaker oppure no?
no, il prossimo è c'è prima Yu Long, cioè, e poi ci sei tu.
Va bene, grazie.
Facciamo un breve coffee break.
Ok, ottimo. Vabbè, ciao a tutti allora, ci vediamo
Ciao,
tra
buon
qualche
caffè Alessandro. Torno a sentirti. Ciao.
Do you hear me? Good morning, everybody, again. And okay. Good morning, everybody, and good evening for Taiwan. And I am Carlo Rizza. I am the chair of this second part of workshop. The first speaker of this second part is Professor Yun-Lun Chue from National Tsinghua University, Department of Material Science and Engineering. In his lab, the research is focused on new materials technologies for nanoelectronics and energy harvesting applications. He received several awards and is editor-in-chief for nanoscale research letters. He published more than 360 papers. Today, the title of his presentation is 2D layered materials toward phase engineered hybrid films for innovative nanoelectronics. I leave the floor to the speaker. Professor Yun Chue. Okay, are you ready? There are some problem.
Wrong with my.
Okay, now it's okay. No. We see your screen, but there are some problem with audio. Please check your audio option.
Can you hear me now?
Yes, now it's okay. No? Okay.
Can you hear me now?
Yes.
Okay.
Now.
Okay. Let me share my slides. I'm sorry, some technical issue from my side. So how about now? Can you see my slides? Can you see my slides? Can you see my slides? I don't know what happened.
Sorry. Okay, do you hear me now?
Yeah, I can hear you.
Okay. Yes, I can.
Okay. Can you see my slides now?
Okay.
Yes, I can.
Okay.
It's okay.
Sorry, there's some technical issues. Good afternoon from all the professors from Taiwan side. Good morning from all the professors from the Italy side. It's very honored to be here to introduce my research activities. My name is Yun Chue. I'm from a Department of Material Science and Engineering, National University. Let me see. Okay, so before my talk, I would like to quickly to go through about where is Tsinghua University. Since you are in Italy, so I would like to introduce the position of our university. We are located in northwest of the Taiwan. Here's Taipei, And in our departments, we had the 5 buildings. We are the first material science and engineering in Taiwan. We established 1972, and then our research normally is in this building, material science and technical buildings, about 45 years old. And now this is Delta building for all the faculties. We have the 2 laboratories. One is for the so-called material science laboratories for all the facility inside, and also we have a lower laboratory for all the metallic processing. We also have new laboratories in the rear side of our campus. And in terms of our research field, we have the accessory research field. So from the biomaterials, for all the materials, you can see this is a typical material science and engineering research work. And in terms of the students and alumni, the number of students in our department around about 800 to 900. 50% belongs to undergraduate students. 50% belongs to PhD and master students. So students graduate from our department around about 6,000, more than 6,500 students. And in terms of academia performance, we are ranking 47 in terms of the material science. Okay, so I would like to go to my research activities because I spent a couple of years on growth of the 2D materials. So because several speakers, including Taiwan side and the Italian side, talking about the 2D material here, just mention about the advantage of the 2D material because very high electrical conductivity and also controllable mobility depends on what kind of material you select from your side. Another important part here is 2D material can have very high service to volume ratio and also very high flexibility. If you look at these slides, you can know about the 2D and the graphene can have very high strengths, limitations without any deformation. This is why a lot of research activities utilize those 2D for all the applications, including photo detector, solar cell, a gas sensor, and CO2 reduction and hydrogen reactions. So before I introduce my research work, I will just quickly go through about why the 2D is so amazing because it's a kind of the polymorphic materials. It means that as long as we control the staking sequence, we can control the physical property from the mechanical transfer behavior to semiconductor behavior. For them, hexagonal normally is semiconductor, tetrahedral symmetry normally is metallic behavior. So the way to synthesize 2D basically can be categorized 2 directions. One we call it top-down. So we use a Scotch tape to mechanically export our 2D counterpart to 2D sheet. But the problem here, we cannot control the number of layers and also the size of the those 2D is quite small. So it's why people think for the other way called chemical or electrochemical exploration process. What they are doing here just introduce the metal cation or hydrogen cation to become atom to do the mechanical electrochemical exploration process so that we can get about mass production of the 2D sheet in the solution base. But however, during the mechanical or electrochemical exploration, they have some damages happen. So this is why it's not good for the electrical properties applications. So the other way here we call the bottom-up method. So the typical we call the chemical vapor deposition process. So what we should do here, we just prepare the metal oxide precursor and the chalcocite precursors and then high temperatures. 2 precursors become vapor, then it will be through the so-called condensation process to form a triangle shape, which is a single crystal 2D materials on the low temperature regions depends on substrate used to have different quality of the 2D materials. But however, the temperatures to gross those 2D materials quite high, normally it's more than 500 Celsius. And also if you want to have the further electrical and functional device applications, you need about transfer processing. Let's talk about a transfer process. This is a typical way, no matter we use a graphene or 2D material, you should use a PMMA to transfer, to aging transfer how 2D to the silicon substrate or any other substrate you want. But it's difficult to transfer those 2D material on the nanostructural surface because if the surface has very high surface to volume ratios, the coverage somehow is not good enough. So the goal in our lab is try to grow the 2D without any transfer and also want to form a 2D at low temperatures. So our idea is from as long as we we want to have the precise layer controllability. If we can also have a controlled phase, for example, metal oxide and the metal dichrotonide, that will be much better to have the more functional device application. So we start to deposit metal oxide, and followed by the so-called post annealing process. For example, if you use a selenium, we call post selection process. If you sulfur, we call post sulfation sulfation process. If you use a telluride, we call telluriation process. We can form a metal telluride, metal ditelluride, metal disulfide, or metal dicyanide layer structures. So we start based on this idea to demonstrate the idea so-called laser radiation assisted selection process. What we are doing here, we use selenium powders in the glass tube, and then put the deposit tungsten oxide on the silicon oxide substrate in the near side of the tube, and nearing at about 250 to vaporize. Our selenium powder becomes selenium vapor. Vapor will be pushed to the other side. As long as we anneal the metal oxide, such as the tungsten oxide, we can form the tungsten dicyanide directly. This is the first time to demonstrate the formation of the tungsten dicyanide at low temperature. And although the device somehow is not good, the mobility is always below 1. So furthermore, we just demonstrate the other way. Can we form the tungsten other sulfur base? The answer will be yes. So we also use thinking the other way. For example, use a solution base by sleep cold. Some sulfur atom in some solvents, we're still able to combine metal oxide, such as tungsten oxide and monoxide, reacting with sulfur atom to become tungsten disulfide, ammonium disulfide. This is a result from our side. As you can see, we can successfully demonstrate the formation of tungsten disulfide, ammonium disulfide by so-called laser annealing processing. So basically, this is transfer-free. So, and also this is a faster selection process. You just in about 10 to 15 minutes, you form about the thing you want. And the other thing, we also think about, can we control the stability? So as we know about, basically, if you just nearly at very rapid temperatures, we can make sure the formation of the 2D material will be the staking consequence will be changed from the horizontal to vertical staking. So idea here, we just use so-called micro assistant selection process. What we are doing here, we just use a silicon oxide deposit the tungsten oxide on a silicon oxide substrate. Then nearby our selenium vapors, then we use silicon carbide as a source to then use micro to heat our selenium powder and also substrate directly. We can form about tungsten dicyanide directly. So as long as we control the tungsten oxide with more than about 20 nanometer, we find out the staking sequence of tungsten dicyanide normally vertical staking. If you reduce the thickness of tungsten oxide below about 20 nanometer after microwave treatment, the staking sequence normally parallel horizontal staking. So the different staking somehow can create different functional application. For example, we can use this for the gas sensor application. This is the red dot will be the horizontal staking. The vertical the square symbol represent the vertical staking of tungsten dicyanide for the gas sensor applications. So, but even we use a laser and also the microwave treatments, we can have a larger scale. So we are thinking about the other way to have the mass production and precise layer controllability. So we just develop the other way called the plasma assisted chemical vapor reaction, so-called PSVR. So the idea will be based on the laser annealing and microwave treatment. So we start from the deposition of the metal oxide first. So then we just use this is a homemade facility in our laboratory. So we have the selenium tank behind the main chamber. So as soon as you heat the selenium tank, you can make a selenium powder become selenium vapor, then carried by the channel to the main channel. At the same time, you use the ICP coil to analyze your selenium atom becomes selenium radical, so that you can form about the 2D material at very low temperatures. For example, without plasma treatment, the lowest temperature to form a tungsten dicyanide is about 500 Celsius, confirmed by the Raman spectrum. If you look at the A1G peak, if you apply the plasma assistant process, the lowest temperature for the formation of the tungsten dicyanide alone can be down to about 250 Celsius. If you look at the microstructures, although the grain size is still very small, As long as you increase the formation temperature from 250 to 500 Celsius, you can achieve about tungsten diaselenide with large grain size, normally about 50 to 100 nanometers. So they have a lot of research in my group regarding fundamental material science, electrical functional devices, energy harvesting storage applications have been published in our group already. So if you're interested, you can go for this from our website. And also, we also find the lower temperature compared with conventional CVD process. So, for example, for tungsten diaselenide, for ammonium diaselenide, tin diaselenide, platinum diaselenide, tungsten disulfide, around about 5 to 700 Celsius. By utilizing our PCVR, we can reduce temperatures at least around about 3 to 400 Celsius. And this is a demonstration of how we utilize PSCVR to grow the tungsten diaselenide. As you can see, if you deposit tungsten oxide by 5 to 7 nanometers, after desalination process, we can achieve about tungsten diaselenide about 6 to 8 layers by reduce the thickness of the tungsten oxide into about 2 nanometers. After desalination process, we can achieve about more layer of triple layers tungsten diaselenide. This is called the layer controllabilities. And this layer controllability had a lot of optical property applications. At the same time, as long as we patent tungsten oxide, after desalination, we still can patent tungsten diaselenide. So, and then we also try our best to measure the mobility. Unfortunately, the mobility is still not good at all. At 250 and even for the 500 Celsius, always below about 1. So we still try our best to optimize conditions to make sure this process can be suitable for electronic applications. Okay, and another part here, this is a scalable process. As long as we enlarge the size of our chamber, we can demonstrate the 4-inch wafer growth. So, and we also can utilize this process to fabricate a 2D material, for example, tungsten diaselenide on the low flexible substrate. This is a demonstration of a growth of tungsten diaselenide on the PI substrate because temperatures normally should be below about 300 Celsius. And now we extend the size of our growth chamber to about 30 to 40 centimeters square because we want seeking for industrial application based on our technique. The idea we can have such low formation temperature because because we just make the selenium vapor become selenium radical. For the selenium vapor is a trigonal phase, and it will be a larger cluster. After we just create the bondings, so we call it crack selenium. So the size of this selenium cluster is quite small, so we can have much higher chemical reactivity. This is why we can form the metal diaselenide low temperature. And one very important feature from our facility, as long as we control the different ambient gas, for example, hydrogen and nitrogen with different ratio, we can also control the conversion rate between metal oxide, metal cyanide, and metal oxide, for example, tungsten diaselenide, tungsten oxide. So if you just have the high concentration of hydrogen and a too low concentration of hydrogen, the ratio, the conversion ratio between tungsten diaselenide and tungsten oxide will be changed. And the result also can be confirmed by our TM result. For example, if you had the pure hydrogens at the same conditions, almost 90% tungsten oxide can be converted into tungsten diaselenide. If you just reduce the hydrogens to the nitrogen about 1 to 1, about 50%. So at the same conditions, we can have the mixing between tungsten oxide and the tungsten diaselenide. If you further to increase the concentration of nitrogens, it's difficult to convert tungsten oxide to the tungsten diaselenide. So why we want to do this? Because we can create a heterojunction. Such a solution somehow can enhance the sensitivity for the phase sensor. This is for example, if you do the 70% tungsten oxide and 30% tungsten diaselenide, we can have a much better chemical, can be act as a chemical resistor for gases application. For example, NUX is one of our example for this case. So for example, we can have about poly 3 PBB, sorry, 3 PBB to be 30 ppbs with an average of more than 10. This is the smallest chemical sensor in the world so far, due to the formation of a heterojunction between tungsten oxide and tungsten dicyanide. At the same time, we also working on a gray-cell development system because we want to create a three-dimensional structure, because after this we can do the PACVR to create a 2D surface on three-dimensional structure. So this is a so-called gray-cell development system. What we are doing here, we just control the rotation angle of the substrate and also control the incident vapor flux. We can grow different hierarchical structure. This is so-called shear shutting effect. Okay, so because it's a coming atom somehow will be the mask to block the following formation of our following deposition of the fin, so that we can create a different hierarchical structures. For example, we can have the so-called VBA structure, nail rod structure, nail rod with a tilting structure. In our lab, we have successfully to demonstrate the growth of the nail helix, nail screw, and the nail rod on different metal oxide systems. And for this part, we further to demonstrate the tungsten dicyanide 2D, 3D nanostructures. What we are doing here is a gray-cell deposition system to deposit tungsten oxide nail screw, and followed by the plasma selection process to form a tungsten dicyanide tungsten oxide. So this is a typical excellent result from my slides. So, and this is a very so-called industrial application, because we can scale up the overall size to about 4-inch wafers. So we also figure out very interesting phenomenon that by control the different plasma power and also temperature, we can control the phase. We figure out the 1P phase will be dominant at low temperatures and high power, while the 2H phase somehow will be dominant at the higher formation temperatures and lower plasma power. So we also convert by SPS and also the TM result, as you can see from my slide here. And such, the 1P and 2H phase somehow can create the other interesting shortcut very high to enhance the gas sensor application. So this is why we optimize the formation temperatures. We figure out at the 150 watt plasma powers, then the gross temperature about 450, we can have the maximum performance utilize this material as a NOx gas sensor. So we also further to calculate the ratio between the 1T to 2H phase with the optimal condition, which is about 46 by SPS result. So the idea here, we can have such better performance due to the formation shortcut very high between the 1T and the 2H phase, due to the difference on the Fermi level and work function between the two phases. And we also further to optimize the height of our hierarchical structures. We figure out if you increase about 60 nanometers, we have the best performance. This is why we can have the best performance of our material for the sensing, especially NOx, about 50 ppb, which is the lowest record in the world so far. And furthermore, we also work on the energy storage applications, and the other will be energy harvesting applications, such as hydrogen fusion reaction applications. So people think about what formation 1T will be the way to enhance the hydrogen fusion reaction. So we want to combine the other two ideas. One, we can have the more active sites, and we also have the so-called electronics conductivity engineering. And then this is why we want to create so-called 2D, 3D feature structures to enhance our water splitting applications. So idea here, we use a gray-cell division to deposit molybdenum first, so we can grow nanostructures, followed by the plasma system selection process to form the molybdenum core and the molybdenum dicyanide as a shear nanostructures. This is a typical picture show my slide here. And if you look at the TM result, you can see that at the 400 Celsius, we can form about the molybdenum dicyanide as a shear layer, where the molybdenum as a core inside these nanostructures. And the overall result can be scaled up to about entire 4-inch wafer. If you detect about from 0.9 to 0.1 to 0.9, they have the same behaviors. Low result be confirmed by the Raman spectroscope, and we further to confirm that whether we can have a 1T or 2T phase. The answer will be yes. If you do the annealing temperatures from the low temperature to high temperatures, we figure out 1T phase that still be dominant at low temperatures as long as increase temperature to high temperatures, say about 550 Celsius, the 2H phase dominates. So this is why we just optimize the condition. We figure out 400 Celsius will have the best result, so that we can have the toughest load about 34.7 millivolt per decade, and it is very stable. As long as we do the 1,000 cycle, the performance doesn't change too much. So such excellent hydrogen resolution reaction is due to the very high density of active site, and with a 1T phase in our monomer dicyanide. And on the other hand, monomer core also play important role as a channel material. So that electron can be transferred through monomer to the surface of the monomer dicyanide to have the much better hydrogen resolution reactions result. If you want to go through the detail, please go through the paper we published 5 years ago. Then we also last year we also used a similar structure for the batteries. So we figure out this is also good for the battery because people think about 2D material also very good as a catalyst or material for the battery. So what we do here, we just use a 2H phase. We just do the PACVR at high temperature to form about molybdenum dicyanide and molybdenum closure structure. But at this moment, we want to make sure this molybdenum dicyanide will be a 2H phase. So result be confirmed by the our SPS is indeed a 2H phase at high temperature. So then, and based on this, we can have a very high capacity performance of battery. The capacity can be around about 380 milliamp per gram at the charge rate about 1 milliamp per gram. If you just increase the charge rate about 5 milliamp per gram, we still can have the 1 milliamp hour per gram, and also current efficiency still can maintain about 100. And furthermore, we also demonstrate the flexible and structurable behaviors because our nanostructure can bear with some tolerance. So this is why we want to demonstrate flexibility of our 2D material for the aluminum-ion batteries. And I want to take a small time, short time to introduce about the other research activities on growth of high quality 2D material. We call it chemical vapor deposition system. In our lab, we can specify to grow different kind of 2D material, such as ammonium disulfide, tungsten disulfide, ammonium dicyanide, tungsten dicyanide, and so the best result so far for the ammonium dicyanides, we can have the mobility around about 20 to 15 centimeters square per second, and we can the maximum size we can about 1 centimeter square. So we also develop the other way called a position controllable transfer, so we can precisely transfer 2D with different twist angle. So we want to looking for the very interesting physical property on those twist 2D materials. So this year we also developed the other way called a wave transfer process, so that we can have a wrinkle-free transfer process to transfer our ammonium disulfide to the silicon oxide substrate without any formation of wrinkle. So mobility can up to about 13 centimeters per second, and the result will be published in advanced functional materials. And here I just want to say, because this new material is very important, so that based on the PACVR and the CVD, we can combine two ideas together to have a so-called Jones structure, because this is a non-symmetry behavior on the monomer disulfide or the monomer dicyanide. For example, we are successful to demonstrate the growth of the monomer disulfide cyanide by modifying the plasma power and the cyanidation temperatures. We can replace the single layer monomer disulfide into the monomer disulfide cyanide. This is called Jones structure. At the same time, we also combined the GLD and the PACVR to have other very interesting materials. For example, semiconductor 2D, metal 2D, superconductor 2D, ferroelectric 2D, and alloy 2D, and hyper and nano wise. Okay, so thank you very much. I wish through my very quick introductions, you can understand what I have done before. If you want to more detail, please scan the QR code to know about what my research is. And I wish through this introduction, I can find a collaborator to have a proposal together from this bilateral conference. Thank you very much. So anyway, so I want to, this is final slides. Welcome to Taiwan. This is a lot of fascinating place. If you come to town, I'm very happy to bring you to those places and have fun together. Thank you.
Okay. Thank you. We thank the speaker, Professor Chue. It's now the time for a couple of questions from audience. You can raise your hand, or if you want, you can write on the chat. Please.
I apologize. The reasons background has some noise because I attend the other conference. As I mentioned, the Professor Lee already, because they have the same conference holder in Taiwan. This is why I attend conference on the same time. I attend this bilateral workshop. Okay. If you want to know about detail my research, I'm very happy to have the other website meeting together. Okay.
Okay. Any questions from audience?
Sandro.
Yes, I have one.
Alessandro.
Time. I'm just curious to know actually what is the difference from the two different methodology for the growth of materials. So on one side is the plasma assisted growth, and on the other side is the CVD, is the chemical vapor deposition.
Yes.
So what is actually the main pros and cons of the two approaches? What you can find best in one that's it's missing in the other, and vice versa.
Yes, thank you. So reasons I want to explore two kind of directions here, because normally for high temperature ones, you can grow high quantity 2D, but we cannot have a scale up to about wafer scale. But the PSCV are here. We want because for the back end process, we need about fabrication temperature less than 400 to 500 Celsius. So the typical CVD process now it should be impossible if you want to have a direct growth. This is why I want to try to think about the other way. Can we grow the 2D at very low temperature, say below about 400 to 500 Celsius? So plasma assistant process can help us to grow such 2D at very low temperature. So we can grow 2D on a wafer scale device directly. At the same time, we are seeking for, because those 2D somehow have some defects. Those defects not good for transistor, not good for electronics, but good for the functional device such as the fault detector, gas sensor. We still have a chance to find those things for following device applications such as more and more. Okay. So the other feature here, just say we can grow different hierarchical structures based on our new so-called gray-single defense system. So we can grow different metal oxide following by the plasma selection process to form a 2D surface on 3D structures for the different device applications. Okay.
Okay.
I'm very apologize because there's something wrong with my headset. This is why I cannot use this at all. So this some noise behind me because I'm in some hotel. We just finished the conference. Yeah.
Don't worry. Okay. Okay. Any questions from audience? No. Okay. It's now the time for the second speaker.
Thank you very much. Appreciate it.
Thank you again very much for your very intriguing talk, Professor Chue. Thank you. Okay, now it's the moment for the second speaker. The second speaker is Dr. Alessandro Molle. he is a researcher of CNR. Sorry, one moment. Okay, from Institute for Microelectronics and Microsystem, Agrate unit, and to take his talk is two-dimensional scenes and related material by epitaxy. I leave the floor to the speaker. Alessandro?
The microphone.
The microphone, please.
Okay. I'm sorry because can you hear me right now?
Yes, I can.
Okay, because when I share the sharing, stop the microphone on. Okay. I'm gonna try to stick to the time scheduling, and just briefly comment, talk about the two-dimensional scene related materials by epitaxy. This is the kind of materials that we develop in our unit, and it's only a part actually of the two-dimensional materials growth and production involving all these collaborators. In particular, me mention Christian Martella, who will be the speaker on tomorrow's session about the TMD's production and nanoscale engineering. But for what regards the introduction of the two-dimensional scenes, so let me make some historical overview starting from graphene and from the other 2D materials related, in the sense that graphene is a semi-metal, so that it's open to be complemented by other materials that are metallic in character, semiconducting in character. This is the case of the HBN, it is insulating. And TNDs, as recently exposed, are a perfect candidate for semiconductors. Actually, they are not actually semiconductors only because they encompass a lot of phase inside, and they displays also topological topological features, but also other non-trivial quantum states such as the charge density waves and so on. But in all this overview, so today I would like to focus on the X-scenes because they are basically the natural followers for graphene, because they are monoelemental in character, even if they are not structurally similar to graphene, in the sense that the graphene is perfectly planar. It's an hexagonal lattice that is flat, but the X-scenes are not so flat actually. They conserve actually the hexagonal character, but they are buckled in the sense that they should be vertically displaced in order to keep all the atoms together. Okay, let me say that the first generation of X-scene, started from the group 4, the same group of carbon in graphene, but included the silicon, germanium, up to lead, very recently. And nowadays, actually, the family has flourished and enlarged so much, just in comprising the boron group with the barphine, with the galanine, but also the pentagen. And for the pentagens, there is a particular interest because I know that in this symposium, this workshop, so there will be actually some attention paid to the phosphorine, to the black phosphorus. Black phosphorus is not the only allotropic form actually to be present in the 2D materials framework, but of course it was actually so much interesting for a lot of applications in mind. But on the same group of phosphorine, there is also arsenine, antimonine, and bismuthine. And recently also there was an interest increasing on the chalcogens, on the two-dimensional chalcogens, including selenine and tellurine. Okay. I'm going to try actually to talk about the X-scene evolution, just in order to give you a roadmap of how we started and where we are directed to, which are our horizons, starting from the single layer and going down to the multi-layer, and to the possibility to put to mix, to pile up X-scene layers together in a heater structure, and also talking about actually stand stabilization issues, because one of the main issues of these materials is that they are not stable under environmental conditions, so they should be stabilized, encapsulated, and so on, just in order to further up practical application. Okay, let me say something about actually the epitaxy. Okay, epitaxy is not the only methodology to produce X-scenes. but it's a more popular one, it's the more used one. And nowadays, actually, there are some chemists, claiming for the topotactical exfoliation with scenes, chemical methodologies that is very, very interesting. But let me say with the epoxy, we are able to control the atomistic structure, the atomistic details. Especially my focus will be on the deposition, so that is the easier way actually to think about epoxy, because we are talking about the deposition of materials on the substrates. But this is not the only one actually, because people around the world actually was talking about the segregation from the substrates just in order to create an excene on top of a buffer layer. But also the intercalation approach is pretty much interesting, just in order to produce a so-called Zintel phase, where the excene, especially silicon, silicon, and germanium, are intercalated in a Zintel compound. Okay, my focus will be on the deposition. So I'm a grower in a sense, and so I will be talking about actually how to deposit some exenes in a portfolio on a different substrates. Let me say that one of the big advantages of the epoxy is to have a large area deposition. So this is a tool to be used actually for the epitaxial methodology. It's an MBE machine. And of course, another advantage is that you can make an in situ monitoring of the properties of the structure, basically the structure and the electronic properties. Here you can see actually a large scale deposition of silicon on top of a 1-1 terminated silver. So the larger area production is one of the big advantages I told you, but it is counterfaced by the fact that the MBE and generally the UHV methodologies are pretty much pretty much expensive. So the cost is a big cone of this kind of methodology. Let me say that according to the silicon, so what we have to emphasize is also the structure variability, in the sense that the silicon is polymorphic according to the different growth parameters to be used in the process. Here you can see actually different phases, and the phases means that it's a structural arrangement of the silicon layer on top of the 1-1 terminated silver that differs according to the temperature. As long as you are changing the temperature, you can find actually different periodicities. But what is important is that each periodicity is associated with a specific electronic phase, so that you can modulate the semiconducting phase from the semi-metallic phase. Another case in point that I would like to mention is the epitaxial phosphorin. This is not black phosphorus, and I tell it actually for people working on the black phosphorus matter, such as Maurizio and so on. But the epitaxial phosphorin is pretty much interesting because it's one approach to make a large-scale deposition of phosphorus at a two-dimensional level. And the methodology is pretty much similar to the exenes like silicon and germanium and so on, because you have to make an epitaxial deposition on a crystallographically matched substrate, such as gold with a 1-1 termination. So the epitaxial flow is made of P4 molecules that decompose on the system on the surface, just to self-organize in a two-dimensional layer. Okay, let me just pass over to the possibility to make it multi-layer. This is the case of a silicon multi-layer, and starting from the silicon monolayer on top of the 1-1 terminated silver, you can pile up layers. But there is a disadvantage in this matter, because it's not clear if we are able to make a layer-by-layer growth, because there are some domains growing three-dimensionally. By the way, actually, we tried actually to integrate to make this kind of growth. We were able actually to discriminate two different regimes according to the temperature. In a certain temperature that is in between 200 degrees and 230 degrees C, so we were able to identify the multi-layer silicon according to the Raman spectroscopy and to differentiate it from the diamond cubic electropic phase that is more common for the silicon bulk. Okay, let me now turn to something that is pretty much recent in our research developments, and this is the heater scratcher. So you know that Van der Waal heater scratcher is pretty much popular in the framework in the field of 2D materials, because they enable us actually to put 2D materials such as the TMDs, graphenes, and so on together, just to expand its functionality. And so the question is here, are we able to make an epitaxial building, an epitaxial production of a Higgs-in heater scratcher? This was not actually so given for granted, because the Higgs-in interacts with one another, and so it's not actually trivial to decouple the Higgs-ins from one another. But this was the case for the heater scratcher made of, silicon and tin, just to have a TSMC silicon heater scratcher. So starting from the scratcher, we in situ monitor the lead pattern, just in order to have a scratcher monitoring of the layer grown, and we were able to deposit the staining according to a method that was previously reported by Yuhara co-workers in Japan. And on top of which, we were able also to find out the difference of the structure. It is pretty much compatible with the silicon deposition, with the silicon layout. So that is why actually we try to conceptualize Higgs-in heater scratcher based on this kind of background, on structural background, so on the lead measurements taken in situ. But even from the Auger spectroscopy, we were able to define that there is a layer by layer discrimination inside the growth sequences, so that it was a case actually to talk about a pile-up of chemically distinct Higgs-in layers. And that fashion was even possible to be reversed, in the sense that we are able actually to put first the silicon and on top the staining. Okay, this was also grounded by some theoretical ab initio calculation, but what I would like actually to focus here is that, okay, we have actually this kind of portfolio of materials, starting from the Higgs-in with several, flavors, the silicon, the germanium, but other people in the world are able to produce the graphene, the tellurine, and antimony, and so on. But are this stable in air? Because if you want to apply that in in technologies, so you need actually durable materials for durable devices, for instance. And so our idea was to cap them with an encapsulation layer, such as the aluminum oxide. The aluminum oxide is pretty much popular in nanoelectronics because it's a typical, insulating gate insulator. Okay, in electronics, it's not the only one for sure, but it's somehow replacing the silicon oxide actually. And as a sequential growth step after the silicon or the Higgs-in deposition, so we found out that the aluminum oxide deposition at a relatively low temperature, I'm talking about the room temperature or a little bit more, so was effective in encapsulating the layer without affecting the chemistry, so that the Higgs-in layer was preserved and the encapsulation layer protects the layer from extraction and transfer in environmental condition. And this is pretty much demonstrated by this kind of Raman peak taken actually from the encapsulated silicon here. Also, the chemistry is pretty much demonstrated by this X-ray photoelectron spectroscopy here. Okay, what is the meaning actually to let you know something about the flavors of this kind of work and this kind of effort to encapsulate the layer, to graph the layers, and so on. So the driving idea is to make use of these Higgs-ins for any kind of possible application. So this is one of a possible representation about the synthesis of bendable membranes. But let me start actually from the first approach here, the synthesis, the delamination, because most of the time actually it's not useful to take to utilize the silver substrates, because it's not actually practical for feasible application, for electronic application, and so on. So that we need to have a membranes. And the membranes is this sandwich where the silicon or any other Higgs-in is encapsulated between a silver layer that is basically playing the role of the templates, and aluminum oxide on top. So we are able to manipulate this layer, and also we are able also to scratch this layer up and down and from left to the right. So in order to create wrinkles, and in order to see that there are actually distortion in the vibrational modes. But I'm afraid I have no time to get into this part. So please believe me when I say that these kind of layers can be stretched in order to deform the vibrational spectrum of this layer or the material itself. Another application that I would like to mention here is that we can keep on, processing the layer and then manipulating the membranes just in order to deposit them on a target substrate, on a device substrate, let me say, just in order to make a transistor, for instance, or any kind of possible, device that you have in mind. And this was the case for the single layer silicon transistor, but also for the multi-layer silicon transistor, where we first evidenced the fact that the silicon behaves as a semi-metal, or at least a certain phase of the silicon, in the sense that there is a pretty much graphene-like behavior that is corresponding to a Dirac point here with the linearly dispersed bands. The case of the multi-layer silicon is a little bit different, because in this case, actually, the curve is not so sharp, but there is still a semi-metal behavior because there is no gap appearing in the electronic characteristics here. Okay, I'm quite at the end on my talk, and let me also mention the other possibility to make a manipulation, processing of this kind of external layers, because previously in this, process flow, I was talking about a dry transfer, but there is also the possibility to make a wet transfer by the chemistry, and the wet transfer is basically made of a chemical action bath where the external layers is practically, decoupled from the substrate, so just in order to have a fission of the membranes that can be, translated and transferred to any kind of other substrates by, quite usual methodologies. And this was actually the background allowing us to transfer the silicon on top of the ITO or on top of the moly disulfide, just in order to create several new fashions of a heater scratcher or hybrid heater scratcher, where the silicon can be put wherever we like to deposit it for any kind of applications that we have in mind. So this is an enabling technologies to be developed more, just in order to create the more feasible configuration for technology deployment, but it's a starting step. And let me conclude by telling you something about actually the overall, picture, the overall framework that I have the pleasure to show you today, starting from the synthesis. And the synthesis is pretty much, complicated by itself, because it may include mono, multi-layer heater scratcher, but also ending up in bendable membranes. And the idea is to make a processing just to have these kind of materials ready to use for applications, and also a final products for the testing in a relevant technology. And this processing is open to the whole portfolio of XCMs, because they are basically mined by the same disadvantages, for instance, the instability and so on. But the key point is that in the XCM family, you can find a lot of electronic flavor, in the sense that you can span from the semi-metal, characters to the semiconducting to the topological insulator. And even if you increase the thickness, so there are pretty much interesting cases in which, for instance, some kind of a heavy XCM may present some non-trivial topological phases. Okay, let me mention actually the founding agency, especially foundations in the Milan region, but also the European Research Council for the granting of my ERC projects. Okay, and let me thank you for your attention. I'm here ready to answer your questions and comments. Thank you.
Okay, thank you, Alessandro, for his very intriguing talk about this new possibility, these new materials, an alternative strategy of graphene and standard materials. It's now the time for question. If you want, you can raise your hand. Okay, maybe we have a question from Federico. Federico, please, your microphone. Microphone is okay. Federico, do you? Do you hear me?
Let's skip to the next question.
Okay. See, yes. Other question?
Anyway, I'm here actually to answer by chat also, so that so feel free actually to post questions whenever you like.
Okay. I have a question. Is it possible? I am not an expert about the fabrication techniques. I am a theoretical physics, but I have a curiosity. Is it possible to obtain a chiral structure where we have a tilt? No.
What do you mean by chiral structure? So because okay,
so when the two layers show a tilt.
Okay,
an angle.
You mean a moire pattern? You mean twisted layer?
Yes, twisted layer. Yes.
Okay, the twisted layer, a very interesting topic actually, indeed, as an evolution of the Van Brug's hydrostructure. So making a twisted layer means that you have to put one layer first, and then you can tilt the second layer on top with a kind of tuning of so-called magic angles in order to unleash several properties that came out from the particular arrangement of the two layers coupling. Okay, in this case for the epoxy it's a little bit more difficult because you have to grow materials. And so it's difficult. So the driving force for the growth is the crystallographic matching, so that you can force the nature to make a tilt. This is possible actually in the Van der Waals structure because basically you make an exfoliation, and so the exfoliation can be mechanically distorted as much as you like. But in the case of the growth, it's pretty much difficult to create an arrangement of this kind. What you may have actually is some kind of a natural, coupling between two layers, so that you can grow one and another one on top. Of course, you can basically tune the growth parameters so that you may change the structure in a temperature window that allows you to have this kind of materials growth. And in that case, you can find actually that there is a moire pattern taking place. But it's not possible to tune it because they are not actually basically decoupled from the in the mechanical exfoliation processing. Okay.
I understand. Thank you. Yes. You are very clear. We try again with Federico.
Yes. Can you hear me now?
Yes, I can. Okay.
Sorry. Okay. So great talk, and just a question about tailoring. I can read it there. So is it a surface that you can actually grow? Have you ever grown?
Okay, thank you for the acknowledgement. Yeah, tellurine is one of the possible materials to be grown. For the direct questions, so I can say yes completely, but we are into.
Okay, cool.
Okay. So the only point for issue that I can find on the tellurine is that I don't really know if we are able actually to bring it into the very two-dimensional layer, because it's very new actually, and so there is no report about the stability of the tellurine. But I think that the tellurine can be even easier to be grown from other materials because it can be also synthesized by CVD, so that there's a quite good expectation for it. But as I told you, I'm into.
Okay. Thanks.
Thanks again, Alessandro, for your very nice talk. And now we move to the third talk. Now we have Gianluca Fiori. He's a full professor of University of Pisa. And his research concern on nano device based on novel materials, and the title of his talk is Electronic Application Enabled by 2D Materials.
So I hope that you can see my screen and that you can hear me.
Yes, we can. Okay.
Yes. Okay. So thank you for
the floor is yours.
Thank you. Okay. So thank you for the introduction. Thank you for giving me the opportunity to present my research today. So indeed, what I'm going to do is to try to show an overview of what could be the potentials of two-dimensional materials for electronic application. Talking about two-dimensional materials for this kind of application, I mean, it's really can open really wide scenarios. Today, I'm going to focus my attention on flexible and wearable application. So the motivation and the visions of exploiting two-dimensional materials for wearable and portable application is coming from this motivation. I mean, today's the technology and all the products are rigid and not customizable, and we would like instead to have, hopefully in a near future, something that indeed is flexible, foldable, and also customizable by the user. So the two-dimensional materials from this point of view can be the enabling technology because they have better performance in terms of mechanical properties as well as electrical properties as compared to what is as compared to the current technology, where I mean exploiting organic semiconductors and so on, that they need as in principle worse performance as compared to the two-dimensional materials. And the other aspect is that it's indeed an added value is that the fact that you have a lot of plethora of material that you can pick up with different properties, semiconducting, conducting, insulating, and last but not least, that you can even think of or arranging in heterostructures. So the idea is to exploit two-dimensional material-based inks provided by Manchester University, in particular from the group of Professor Cinzia Casiraghi, and to try to develop a kind of an electronic device toolbox where one would like to obtain the different devices and parts that are important for the electronic application. So, I mean, I'm talking about passive components like capacitors, and then nonlinear and active devices like field effect transistors. One is able to obtain this, so the target is to combine them in more complex circuits, like, just here to give some example, a CMOS amplifier or even memory. And once you have that, to move further and try to develop an integrated circuits like the one that we are trying to develop here in the WASP project, where the integrated circuits can be put on top of an appendage, for example, and then is able to detect some and to analyze some important information like temperature, the pH levels, as well as glucose level, and then to deliver this information to a simple reader that can be, for example, a cell phone. So not only this technology wouldn't open, let's say, new scenario, not only in the portable application, but also, for example, in anti-counterfeiting, as well as the other application like in the food market, in order to detect product freshness and to deliver directly information about the food that is packed in some packages. So where are we now, and what do we need? For sure, the ones that are enlisted here are the main ingredients that need to be solved, and you need to start with in order to to cook your device and circuits. First of all, you need good resolution. So what does it mean, good resolution? So if you go back in the 1970s and you look at the Intel, one of the first microprocessors, the Intel 8008, the resolution, the lateral resolution of these devices, this chip was around 10 micrometer. And this was done on top of rigid substrates, the silicon. And this is nice. The nice thing is that now we can obtain the very same lateral resolution, but on top of flexible substrates like paper. This is something that, for example, we are trying to achieve and we go beyond this resolution with a prototype that we are developing these days, that is able to go beyond the 10 micrometer lateral resolution. So to obtain, these kind of structures on flexible substrates like paper, and this, for example, would represent the source and the drain. So you deposit the semiconductor on top, and you can have scaled, really micro scale devices. This, in this case, is an example of a 3 micrometer channel device. Then you need obviously good electrics, and you need to good electrics in terms of also the possibility to work at the low voltage application, because when you are talking about wearable application, would like to have low voltage in order to spare the energy of your batteries. So this is, for example, one devices that we put on top of paper that is probably this is the first fully printed graphene FETs printed on top of paper, so fully printed, where everything is printed, starting from the source and drain contacts, the channel, the electric, as well as the top contact. And we managed to demonstrate a flavor of, let's say, modulation of the current. But this is not due to the process by itself, but this is due to the fact that indeed the graphene is a semi-metal, so and not a semiconductor. So it doesn't have a band gap, so it's completely impossible to switch off the device. So rather than graphene, it's better. It will be better to use good semiconductor, real semiconductors. Obviously, the first semiconductor I chose come to mind is MOS2. The problem is that printing of MOS2 is not that trivial, as it was, clear from the very beginning. Indeed, from this work by Michael Ossi and Max Lemme, it has been shown that the current cannot be modulated, and most probably because of the large numbers of defects that are present in the network of MOS2 flake. A really nice example of a solution processed deposited MOS2 channel is this one by Professor Duan. The only problem is that the post-processing, like for example the annealing and all the chemical process that has been used, are not compatible, for example, with flexible substrates like paper, that is our target substrates. So it came to our mind to use this approach. So to start from CVD MOS2 and then transfer CVD MOS2 on top of flexible substrates like paper, and then define all the other component of the device only through inkjet printing. So the process is, it can be summarized here. This is a collaboration between us, Manchester, IIT, and Vienna. So there's a transfer of CVD MOS2 stripes on top of paper, and then all the other components, as I was saying, so the contacts, the dielectric, as well as the top contacts are defined through inkjet printing. So here is just a sum up of the process for the transfer. So the MOS2 is grown on top of sapphire, then is patterned, and then is the transfer to paper. Just put it, it's a wet transfer in water, or in the worst case in the KOH. And then the paper as well is fished on top of the paper, the target substrates, and then the polystyrene is removed. And this is a micrograph picture of the transfer device, and this instead of the picture from a microscope, optical microscope of the source and drain, the defined source and drain, the boron nitride, as well as the top contact. These devices are working great in the sense that we have really large current modulations with a limited gate voltage applied below 2 volts. So these, I would refer this to low voltage application. Indeed, good saturation of the current in the output characteristics, and the really high performance in terms of mobility with respect to ion-IF ratio, and already comparable as compared to more mature technology like IXO or carbon nanotubes and organic semiconductors. If banded, the IV characteristics does not change at all, or or really few. That is indeed a really good point in favor of this technology. We have tried also to define, instead of silver contacts, graphene contacts, printed graphene contacts, but the problem is that we have large Schottky contacts, as shown here in the Bernstein signature in the output characteristic of the device. Then we have played a little bit with these transistors, defining NOT port, NAND port, as well as current mirror, that work great, especially the gain is really large. Obviously, we would like to move farther and to obtain something as the same complexity as the one that we obtained in this joint collaboration with the group of Thomas Müller. This research is led by Thomas at Vienna, where indeed an operational amplifier has been fabricated and measured with a complexity of around 12 transistors, and it has been demonstrated to work great as let's say a building block for electronics, like for example trying to use this for inverter amplifier integrators and other let's say main building block for analog application. This is a rigid that we would like then to move to flexible. One thing that I want to underline is that in the previous cases, all the technology was a resistor transistor logic, while in order to obtain really good performance, you would like to have a CMOS technology. So the missing piece is the PMOS transistors. What we have done, what we're trying to do is to integrate the technology that we have shown before with the carbon nanotube technology. So the NMOS by nature, the NMOS by nature behave like an N-type transistors, while carbon nanotubes by nature behaves like P-type. So we have integrated these two different technology together. So everything is printed again, except the NMOS that is transferred. And indeed, likely, we managed to obtain really good matching between the N-type and the P-type that indeed has led to large gain. Again, we have tried to integrate this technology in order to attain really simple circuits, CMOS circuits, like, the most simple indeed is the inverter, CMOS inverter. This is the NAND port that has shown really good performance. And then we have moved through more complex structure, like for example, this is a D-latch integrated the CMOS technology as well as the pass transistors. So from the functional point of view, everything works great. The only problem indeed that still have to be solved is the fact that these devices for the moment are slow. So we need to improve the speed, as I was going to mention in a couple of slides. So obtain, as you've seen, the complexity of this simple chip are around tens of transistors. But obviously, if you want to implement the device that I was showing at the very beginning, the one delivering information for healthcare application, you need to go for really complex structure. So obtaining a fully printed device probably is not at reach yet. But in order to get some results in the short time, probably the hybrid approach is the best one. For hybrid, I mean that you are integrating, let's say, mainstream rigid the technology, silicon technology, but for example, put on top of flexible PCB together with printed technology as the one that I was mentioned. So for example, here in the case of the paper substrates, where everything is printed except these two circuits here, you have the printed antenna, the connection that are printed. Here in this case, you have a graphene sensor that is printed. The IC obviously is not printed, but it's on flexible substrates. And this, for example, is a perovskite solar cell, again, glue on top, but it's flexible as well. So we have tried to develop a proof of concept device. I'm going to show you to describe briefly the functionality. So when the light is off, we have a single strain value that is sampled, and then this is read and delivered back to the cell phone that is interrogating the systems. When the light is on, instead, this works as a multiple strains value log that are sampled and saved on a memory that is placed on the chip. And then these information are delivered back when the cell phone interrogates the chip. So this is a video that is summarizing the demonstrating the proof of concept. So again, so when the light is off, we are making a simple read. The simple read is seen here. So you see the runtime, the counter. This is the counter is equal to 1, and we are reading, for example, 1 value. While the light is on, instead, we have multiple reading, and we see here that indeed the counter, whenever you put interrogate the system, so you put the cell phone on top, is increasing, and then you are reading here the multiple values. Okay, so again, the last thing that we need, the last ingredients that we need is the speed, and there are lots of problems with these. I mean, not only with printable, but also with MOS2 or two-dimensional material in general. One of the main problems that indeed we need to address, and for example, we are trying to address within the flagship, is to reduce the hysteresis. That is due most of to the fact that you have lots of traps, for example, either in the oxide, but also in the two-dimensional materials that are leading to really large problems in long charging time, as well as in huge problems in the hysteresis that need compulsory to be solved in order to obtain a really functional device. So this brings me to the conclusion. I should be in time, and okay, and obviously let's acknowledge my main collaborators as well as the funding for that has allowed us to do this research. So thank you for your attention.
Thank you, Professor Fiori, for his very nice talk. It's now the time for question. If you want, you can raise your hand for questions. Okay, no question from the audience. I have only Federico.
Yes, can you hear me now?
Yes, yes,
okay, so cool.
We can.
Okay, so wearable. So just a commercial question, would say. So you show us devices on paper. So how about texture or clothes? Have you tried to put something on clothes?
No, this indeed it's an alternative substrate to paper. We haven't done this yet, but there are groups that indeed have worked a lot on this. For example, Felice Torrisi has worked a lot on this when he was in Cambridge, and also now that he's in London has done a lot of research on that. I mean, and there are lots of groups that indeed are trying to develop this, so integrate these devices on top of texture, because yeah, indeed you can integrate directly on your clothes, and this could have a huge market. Yeah, that's true.
Okay, that's cool.
Okay, good. I have another question, a curiosity about the transistor, MOS2 based transistor. No, you consider four electrodes.
Okay.
You consider, Antonio? Okay.
Yes.
Okay. Sorry. Okay. You can consider an ink based on graphene. Okay, I understand.
Yes.
That you use this a mix of graphene for electrodes. It's right. Yes.
Yeah, we have tried both. Indeed, we have tried.
Okay. My question is a good choice or is only a cheaper solution?
No. So for graphene, we have tried to use graphene as a channel for the FETs. It's a bad choice in the sense that it's going to work as a semiconductor. So you cannot switch the channel off. As a contact, it can be an option. In this particular case, printed graphene contacts are not extremely good. Because we have shown that indeed we have large the formation of a Schottky barrier at the interface that is detrimental for the transport and is leading to large contact resistance. But for example, this is for printing. In case of let's say CVD, MOS2 and CVD graphene, then indeed graphene has been demonstrated to work in the other way around. I mean, if you use graphene to contact MOS2, this is reducing the contact resistance. I believe because, I mean, morphologically, inkjet printed devices are made of networks of flakes, rather in the other case, it's just one flake. And so you are changing the interaction between the interfaces that indeed are really fundamental for even from an electrical point of view.
Okay, thank you.
Just a curiosity regarding the concentration of the functional links, concentration of the flakes of two-dimensional materials. And another question, if you are interested in exploring new van der Waals semiconductors as those presented in this workshop.
So the concentration here is around milligrams per milliliter. So and so around 1 or 2 at most in the case for some cases. I don't know that for sure. I mean there are lots of. So the nice things about two-dimensional materials indeed is that you have really a plethora of different materials with really different electronic properties. So indeed now it is just a matter of finding the right one for your application. So
yes.
Yeah.
Yes.
So you have in mind an application, then then you have in mind some electrical requirements, and then it's a matter of finding the right material. I mean, and if indeed you can find the correct one, then you are done.
Thank you very much.
Thank you.
Thank you, Professor Fiori. And now we move to the next speaker. The next speaker is Professor Vincenzo Galdi. He's a full professor at the University of Sannio, Italy, and he's an expert in metamaterials and photonics. His research interest encompasses analytical and numerical modeling of wave propagation in metamaterials and complex environments. The title of his talk is Metamaterials, Basic Perspective and Lesson Learned. I leave the floor to the speaker.
Thank you very much, Carlo. Can you hear me? Can you see the slides?
Yes, Vincenzo.
Okay. Thanks again. And good afternoon or good evening, depending on your time zone. So, first of all, I want to thank the organizers. It's it's a real pleasure and honor to be here today. And I come from a different community, so my talk may be a little different from the previous one. So I'm a theorist and I work on metamaterials, mostly electromagnetic metamaterials. So the scope of this presentation, it's in the first part to give you an overview of the basic aspects and also the recent trends in this topic. And then in the second part, I would like to connect it to the some of the topics that may be more of interest in this community. So how this concept can somehow inspire some new developments in two-dimensional materials, so in terms of planar meta-optics with polaritons, and finally some conclusions. So what is a metamaterials? This term has been mentioned also in one of the earlier talks by Professor Cao. Essentially, a metamaterial is an artificial engineered material made of deeply sub-wavelength inclusions, and even if these inclusions may be macroscopic, depending on the frequency you're working on, since they're small compared to wavelength, the material can be still seen as a continuum, and so can be described in terms of effective parameters. And the interesting thing is that most of these macroscopic properties are derived by the structure and are not the arrangement, essentially, are not necessarily limited by the chemistry of the constituent, which allows to lift some limitations of natural materials. So look, for instance, of behaviors, exotic behaviors like negative index materials, or attain some properties that are typically not available at the specific frequencies you're working on. Think, for instance, of optical magnetism. And it is a very exciting research field which blends fundamental science, but also has lots of technological application with a market that it's growing very steadily, and ranges from defense to consumer electronic and energy applications. And although it's an inherently multidisciplinary area, and although most of the results that I'm going to show have to do with electromagnetics and optics, this concept have also resonated in other branches of physics like acoustics and thermodynamics, for instance. So just to give you a couple of basic concepts, let's start with the negative refractive index. So during the 60s, it was shown in a seminal paper by Victor Veselago that although there was no instance in nature of materials which could exhibit, simultaneously negative permittivity and permeability, there was no basic physics law that prohibited it. And he speculated that if you allow this behavior, then something very strange may happen. So basically most of the physics laws like Snell, Cherenkov, or Doppler get sort of flipped. And then in 2000, John Pendry showed that this behavior could actually lead to what they call a perfect length, so something that could, in principle, beat the diffraction limit, at least in theory, if you don't consider dissipation. Also, from the practical viewpoint, this negative refractive index has implications in terms of reducing the size of components like waveguides or resonators. You can make it small compared to the wavelength. So this is very interesting in fields like microwave or antennas. And again, material like that was thought impossible to exist in nature. I'll come back a little later on that. And so, in principle, it can be engineered at different frequencies. Another interesting possibility is the hyperbolic dispersion. So, a material with an anisotropic material with opposite sign components. This allows dispersion surfaces that are essentially hyperboloidal. And it enables the propagation of high wave number modes, which allow the transfer of sub-wavelength details to the far field. and there are many applications ranging from imaging to nanolithography. And again, it was thought that these materials were not available in nature, and so it was proposed to synthesize them as metallodielectric multilayers or nanowires. Another key concept in our community that was put forward again by John Pendry in 2006 is the concept of transformation optics that essentially relies on the covariance properties of Maxwell equation, and it allows in principle to shape at will the flux of energy as long as is it possible to control very finely the spatial inhomogeneity and anisotropy of a material. And there are some examples where this can be done approximately. You may have heard of the so-called cloak of invisibility. This is one of the possible applications. However, from the technological viewpoint, it is very hard to manufacture, three-dimensional volumetric metamaterials. So a big leap in terms of practical application has been obtained by, thinking of the two-dimensional equivalent of these metamaterials, the so-called metasurfaces. There was a seminal paper by Federico Capasso's group in 2011, and they showed that it was possible to generalize the Snell reflection and refraction law by imparting abrupt gradients of phase, so create essentially anomalous reflection of refraction. And if I have to look at the historical path and the trends of where this sector is going, we started around 2000 with what they call the first generation materials that were essentially a periodic structure, and so can give band gap or other type of properties like that. And then about 10 years ago, people started modulating spatially the properties of these materials. This is very interesting applications like antennas, for instance. And now we are in what we call the third generation of metamaterials and metasurfaces. And some of the trends that are, they are actually of interest now is the possibility to control the properties, not only space, but also in time by using tunable or reconfigurable materials. Also to embed sensing and computational capabilities. Also to combine gain and loss by using non-Hermitian concept like parity time symmetry. And finally, since in most engineering application, you don't have only one physical aspect, but you want to control jointly, for instance, the electromagnetic and the thermal response, multifunctional and multiphysics responses are very interesting. I don't have time to go all through these points. I just want to show you a couple of pointers. For instance, there are applications where you can embed sensors in the surfaces so they can also learn from the environment and react to the stimuli of the environment, and so change the response on this basis. Also, for future technologies, for future communication technologies, there is a lot of interest in what are called reconfigurable intelligent surfaces that can create anomalous reflection or refraction. And in principle, you can think of exploiting multiple reflection in the environment at your advantage in order to deal with situations where you don't have line of sight. This is a very hot topic in telecommunication at this time. Also, there is a lot of interest in embedding some computational capability in the metamaterials. In 2014, in collaboration with Andrea Lu and Nader Engeta, we published this paper in Science where we proposed to use a metamaterial to create some, to perform some mathematical operations, for instance, compute derivatives like a second derivative that can be used as a Laplace filter in image processing for edge detection. That was a theoretical paper, but inspired a lot of experimental studies that show the proof of principle. So now there is a lot of interest in performing analog computing using metamaterials. So basically performing on a physical layer some operations that are typically virtualized in terms of software in communication systems, for instance. And recently, Nader and Guetta's group proved at microwave frequency, a proof of principle at microwave frequency, that in principle metamaterials can also be used to solve equations. And they did it with a material that is 3D printable, so it's pretty simple and also easy to scale at different frequencies. So now let me start with the second part of my talk, where I want to show you how this concept could in principle inspire some developments in van der Waals nanomaterials. That we heard also in these presentations today that there is a lot of interest in these materials and in the propagation of polaritons, and there are lots of application to sensing and nanoimaging and so on. Now, natural van der Waals materials typically come in the form of monolayers, thin slab, or even a hybrid heterostructure. Some of the concepts that I mentioned before are also permeating this application. So we're seeing some artificially engineered van der Waals materials where you can mimic some typical effects of planar optics, like junction, waveguides, or cavities, or even something more complex like meta-optics. So concepts like transformation optics or photonic crystal, metasurfaces, moire bilayers, or line waves that are typical of metamaterials are also being investigated in this framework. So just a quick look at these applications. Well, when you talk about van der Waals materials, you want to look at the in-plane dispersion. And depending on the type of materials, you may have like a circular dispersion that basically provides isotropic propagation of the polaritons, or elliptic, that's another typical behavior. It actually turns out that it is possible to obtain hyperbolic behavior even using natural materials. Some examples are black phosphorus, for instance. And usually when you go from a transition, a topological transition between an elliptical and an hyperbolic regime, you go through a flat band regime that provides a very highly collimated propagation regime. Now, as I said, some of the concepts of planar of refractive optics can be applied in the planar regime by putting together some heterostructure. So, for instance, you see here some examples. These are taken from a nice review paper that came out in Nature a few months ago. And so in principle, you can obtain effects like in-plane lensing, or like a prism, or even negative refraction by creating a heterostructure with graphene or HBN and so on. And in principle, some of these properties can be tunable, for instance, using phase change materials or graphene by changing the chemical potential. And indeed, in 2011, there was this there was a seminal paper by Nader and Guetta that proposed the use of transformation optics on a graphene platform. So control locally the properties of graphene to attain, typical effects that we saw in metamaterials. And some of these concepts are actually being verified also experimentally. I say again, I took this example from this recent review paper, so you see that it is possible to shape, to pattern these materials to obtain like nanocavities, also hyperbolic metasurfaces in a regime where it is not possible to find this behavior in natural materials. So you can do it with nanoribbons, for instance, or you can obtain very anisotropic behavior that leads to canalized propagation on a polariton. You can blend the concept graphene with photonic crystals to obtain effects like defect waveguides, or even apply some of the metasurface concept, like the gradient modulation, spatial modulation on this type of van der Waals materials. Another very interesting concept that was put forward by Andrea Lu's group is the moire engineering that was inspired by the concept of twisted bilayer graphene. They show that if you put two layers of a metasurface or a natural surface, then you can exploit the interlayer effects to do dispersion engineering. Essentially, by changing this twist angle, you can have a topological transition between elliptic and hyperbolic behavior. And at the intersections, you basically get the analog of the magic angle for twisted bilayer graphene. So they call it photonic magic angle, where you have a high collimated and diffractionless canalized polarization. And interesting, they did the first theoretical study when they considered some artificial metasurfaces made of graphene with nanoribbons. But then for the experimental verification, they actually realized that they could attain those properties, the hyperbolic dispersion from natural materials, in particular molybdenum trioxide. And so they proved this concept experimentally. The last concept that I want to mention is the concept of line wave. That's essentially the one-dimensional analog of surface wave, except that they propagate in plane, so they enjoy both in-plane and out-of-plane confinement, and they can propagate at the junction between two dual metasurfaces, like one capacitive and one inductive. They have very interesting properties, and their existence has been proved experimentally at microwave frequencies, where it's fairly simple to manufacture. For a capacitive metasurface, you can use patches, and for an inductive metasurface, you can use the dual, so essentially holes. There are some theoretical studies or this concept in graphene platforms, although there is no experimental evidence. And it would be very interesting because with graphene, in principle, it is possible to reconfigure this junction. And so switch, for instance, from like a waveguide to a coupler and so on. Also, there are lots of interesting properties in terms of field enhancement and propagation-dependent polarization, and also some sort of some weak topological robustness. More recently, we showed that this concept can also be extended to non-Hermitian structure by using modulation of gain and loss instead of the reactive part. And there are interesting effects in terms of chiral coupling. In principle, you can obtain a truly one-dimensional lasing and other properties that are typical of non-Hermitian structures, like exceptional points. So I think my time is over. So I just want to draw some conclusions. I hope that you find this this overview interesting, that may inspire some new developments. I believe that cross-fertilization between metamaterial science and material science is crucial because, on my side, we do a lot of speculative research, but then, metamaterials may give some interesting properties, but then when you go to very small scale, when homogenization breaks down, you cannot apply them. However, some presumed meta properties like negative index, hyperbolic dispersion may actually be present in nature. And actually, just last week, in the last issue of Physical Review Letters, there was this very interesting paper, actually from a group from Taiwan, that showed that another possible implementation in natural materials of the concept of negative refractive index. So you don't necessarily need a metamaterial for these, exotic responses. And so let me finish with, citing this quotation that is usually attributed to George Bernard Shaw. As physicists and engineers, we usually look at things that are, and we ask why. But in our community, in the metamaterial community, sometimes we flip this question. So we think of things that do not exist and ask why not. And sometimes you need a metamaterial, sometimes you don't need a metamaterial. So I think the interaction with the material science community, it's very crucial to distinguish, the wishful thinking from something that can actually be done. And with that, I conclude my talk, and I thank you for your attention. I'll be glad to take any question.
Thank you for your talk. It's very interesting. Thank you for this broad overview on metamaterials and photonics. Now it's time for a couple of questions from the audience. Okay, I'm only a curiosity. Line waves, about line waves. Okay, it's possible to obtain line wave with dissipative system, is right?
Of course, you get some damped version. I mean, here I'm assuming the form that was studied at the very beginning is where you have reactive surfaces, one capacitive and one inductive, and there is no closed form solution, contrary to the surface waves. We show that if you have a lossy surface coupled with the gain material, regardless of the capacitive or the inductive behavior, you can obtain localization both in plane and out of plane. Of course, if you have only loss, then you won't have a purely real propagation constant, so you will get attenuation. When you have loss and gain, they can somehow compensate each other, and so you can have actually a real value propagation constant.
Okay, thank you. Another question. Do you know that there are some groups observed this line wave experimentally? Is only a curiosity. With gain or loss? With gain or loss?
No, not with gain or loss. No, so far the only experimental evidence that I'm aware of is at microwave frequency using capacitive and inductive sheets.
Okay. Thank you again for your talk.
Okay, I have a question.
Sure.
Sorry, my question. Okay. Would you show me the slide with the PRO paper published by Taiwanese?
Yes.
Yeah. Okay. I want to know these people, and maybe I can contact these people and learn more about the metamaterials from you.
Yeah, this came out. I saw it like on Friday. It's the last issue of Physical Review letter. It's very, very recent. I actually only had a chance to give it a glance. It's I haven't read it, with great attention, but it looks very interesting.
Okay, thank you.
You're welcome.
Okay. Okay, good.
Much for this recent paper on physical review letters. We will contact these authors surely.
Yeah, for the next workshop, it will be interesting.
Okay, it's a good idea. Okay, thank you again, Vincenzo. And now we move to the last talk. The speaker is Yan-Fun Lee from Institute for Nanoscience, National Tsing University. The title of his talk is Exploring Ultrasensitive van der Waals Materials to Develop Potential Electronics.
Thank you to the committee give this opportunity to show what I do in the past few years. My name is Lin Yan-Fu from National Zhongxin University in Taiwan. My title is shown here. Today I will explore the ultra-sensitive van der Waals material and try to develop their potential electronics. It's a history of my group. I built my group 8 years ago and in Taichung City. In the first 2 years, I tried to study the two-dimensional electronics, one-dimensional electronics, and organic electronics, as shown here. And the second 2 years, we keep the two-dimensional electronics and also develop 2D PN heterostructure. In the third years, I try to develop all 2D electronics, as you can see the results shown here. And now we study focus on 2D material and other interesting low-dimensional material. Okay, it's a publication as function of year, as you can see, increase. My group always focus on study the electrical property in low-dimensional electronics. For the system, as I mentioned, I try to focus on one-dimensional electronics, organic electronics, and two-dimensional electronics. For the strategy, we use the temperature-dependent electrical property to understand the charge transport and to study the nano contact. And I also study the low-dimensional fluctuation, as well as develop the interesting nanoscale application. For the structure, in the beginning, when we take the material, we will study the transistor and then go to the floating gate electronics over memory, and then go to the artificial snaps. It's my outline. In the beginning, I will show you how we will use the 2D material for future electronics, and I will discuss the challenging in 2D electronics, and then go to my topic. My topic, I will focus on indium cyanide material. And the second part, I will use the several works in my group to understand the fundamental something and to understand the charge transistor-based application and understand the artificial biorelated electronics. Finally, I will give you a short conclusion. As you can see, let me understand the electronics revolution 10 or 20 years ago. If you would like to finish one work, maybe you need to prepare the telephone, calculator, typewriter, camera, and so on. But now, you just lie on the sofa and move your finger on the touch panel, and like the potato, you can finish all the functions that you want. As you can see, device size reduced several orders of magnitude. 10 years ago, more than 10 years ago, the device size like this one, you can store several hundred megabyte data, and now you can store several hundred gigabyte, and then it's a very, very big size impact. If you think about the transistor were like people, several years ago, people try to prepare the electronics. They try to put the 2000 transistor onto the 12 millimeter square area. It's like a traditional Munich hole cloud the 2000 people into this Munich hole. And then in 2000, like put the all city member into the same area. How about now? Now actually is more than 1.3 billion transistor into the 10 times of original area. Okay, it's like put the whole China people go into the time, go into the 10 times of original Munich hole. It's very crazy, but we call it's a scale rule of it's a scale of Morse law. As you can see, the device size reduces several orders of magnitude, and the packing density increases several orders of magnitude. There is a limit, the physical limit. We will discuss this physical limit later. And if we consider the Morse law, can it be continued? If you think about this question, you need to think about the planar MOSFET structure. As you can see, here is source, here is a drain. We use a vertical electric field, this gate structure is shown here. We use this vertical electric field to control current on or current off. So for the typical electronics, we want the on-off ratio we want a high on-off ratio, we want a high on current or low of current. Of course, in order to serve the power, we want a very small SS value. Okay, the typical transfer curve shown here is a log scale for the is a left hand side is a log scale and the right hand side is a linear scale. As you can see, of current shown here, on current shown here, the slope indicate the SS value. So we want the on-off ratio is very big and the off current is very small. Of course, the on current should be very large. But for the typical structure, we just select the right material, we can get the function that we want. But how about the short devices or small devices? Actually, for the small devices, major issue is leakage. For the transistor, actually it's like a switching, and we can switch on and we can switch off. However, for the small channel devices, the on current is very similar to the long channel, but off current, as you can see, the off current for the short channel will increase significantly. So therefore, no leakage control is no scattering in the future. How to determine the short channel and the long channel? There is a very special lens. As you can see, source, drain, and the gate is a dielectric thickness, and this one is a channel thickness. And there is a special lens we call the lambda. This special lens relates to the thickness and the dielectric constant for outside layer and the channel layer. If your channel length is similar close to 5 times of lambda, we need to consider the short channel effect. Here, I try to give you a Venn diagram to understand more about this behavior. The y-axis is energy, the x-axis is distance. For the long channel, it's very easy to create a barrier, so charge is not easy to broken this barrier and go to the drain area. But for the short channel, it will meet a very large dipole effect. What is a dipole? Which indicates the drain-induced barrier lowering effect. So as you can see, the electron can very easily tunnel from the source to the drain and make a very large leakage current. Let's consider the traditional materials such as silicon, germanium, or gallium arsenide. If the channel length is only 5 nanometer, the body thickness should be smaller than 1 nanometer, as you can see, like this one. It's not very easy to realize by using the current nail technology. Therefore, scientists try to overcome this barrier. They think about three methods to overcome this barrier. Something like the more and more. So the scientists believe the size can reduce again. So they try to develop the FinFET, multi-gate devices, and so on. On the other hand, they believe they can more and more, which indicate they try to develop promising applications, something like the power-saving devices, bio devices, or optical electronics, or multifunctional devices. They can combine all the function and into the single electronics and overcome the barrier. On the other hand, they try to use another method called the beyond the CMOS method. The beyond CMOS method, scientists try to find out the new material, new structure, and the new mechanism to overcome this barrier. Therefore, using these 3 methods, the scientists believe they can extend the CMOS or extend the Moore's law. So therefore, maybe using the ultra artificially thin layer material, such as 2D material for the next generation electronics would be a very good opportunity. Okay, let's think about the technology node. 7 years ago, people tried to develop the bulk MOSFET, and then they try to reduce the thickness, so they develop the ultra thin body SOI, and then try to got a very nice leakage control, so they try to develop the FinFET structure. And now they try to scientists try to use a 2D material to well control the leakage. In the future, scientists try to stake in those 2D material and then become the nanosheet field effect transistor. Let's consider the mobility as function of the body thickness and the substrate as a function of gate length. As you can see, it's for the silicon electron part and the silicon hole part. As you can see, the silicon mobility will reduce because on the surface there are a lot of dangling bonds. So if you reduce the size, the dangling bond effect will damage the mobility in your system. So as you can see, the silicon mobility reduces very fast. But for the 2D, as you can see, most of the 2D, they always keep the very, very high mobility. Even the body thickness is very, very small. But how about the substrate swing? As you can see, the 2D material, they can get a very big substrate swing. Even the gate length is very small. So consider the technology node. As you can see, in the past 6 years, scientists try to use the silicon, and then now maybe scientists can use a 2D material, or use a gate-around structure, or use the nanosheet field effect transistor, or spin, or quantum something. Anyway, the 2D would be a good opportunity to overcome the future technology node. Okay, so actually, let's consider the 2D material family. There are more than 1,000 2D material in the world, and the most of the part is a semiconductor behavior, the band gap between the 1 to 3 electron volt. Some of them are insulator, and then as you can see, the band gap is tunable as function of their thickness. From the mechanical, from the semiconductor, from the to insulator, and then we can select a different material and the staking together become the artificial vertical heterostructure, and then we can realize all functions that we want. So we want the 2D material become the interconnector, become the electrode, become the channel material, and the staking each other. Eventually, we want our structure can realize like this one. Use a 2D as a CMOS part, use a 2D for the memory part, use a 2D for the photodetector part, use a 2D for the transmitter part, and the staking together. Okay. Let's consider the challenge for the real 2D material. Actually, there are but a lot of challenges. For the material part, how to grow a very big size, how to dope in your 2D material, how to passivate the surface is a very big problem. For the physical chemistry part, how to functionalization, how to understand the carrier dynamic, how to combine the different dimensions into the same position is also a very big problem. For the engineer part, how to develop the O2D circuit, how to make the contact interface problem, how to stake in the different material into the same position precisely is also a very big problem. In my group, I try to focus on doping issue, I focus on passivation issue, I also focus on dynamic issue to understand the charge transport, and we also try to solve the contact problem for 2D electronics. Let's consider the 2D field effect transistor. What target is very important. It's a cross-section of 2D electronics. As you can see, it's a gate, it's dielectric, it's channel, it's substrate. The main problem for the 2D field effect transistor we need to consider, okay, it's our result. We realize my group are taking more than 10 material into the same place. For the 2D field effect transistor, there are a lot of problems. something like this one for one point. How to select a channel is a very big problem. How to select a dielectric is also a big problem. How to overcome the channel substrate interface problem, and how to get a good contact resistance is also very big problem. Okay, I try to give you a table to understand the intermediate, critical, and the long-term target for the 2D transistor. Here, I try to give you a silicon as our reference. Okay, for the silicon, as you can see, the VDD is operation voltage is a 0.65 volt. The subswing, the minimum subswing is on close to the 65 millivolt per decade. The mobility is close to the 100 centimeter square per volt per second. But how about the 2D? For the 2D, actually now, for the 2D, the VDD is too large. The swing can be close to the silicon, but the mobility, actually most of the 2D material mobility is smaller than the silicon. So how to realize the intermediate target and go to the critical target and then realize the long-term target is very important. Okay, let's go to our target, indium selenide. Actually, indium selenide is an ultra-sensitive 2D material. The body thickness, the 1 mile layer is a 0.75 nanometer, and its band gap is about 1.3 electron volt from the bulk to the field layer, as you can see, like this one. And because of effective mass is very small, so mobility from the theoretical position, the mobility is very, very high. The history about this material electronics can track back to the 60 years ago, published on nano later, as you can see, realize the transistor and realize photodetector and realize the electronics on the flexible substrate. But at the last moment, envelope ratio is not very high and the mobility is quite small. How about the challenge for this material? The challenge one is surface oxidation. Okay, as you can see, the surface, the oxide and the oxide or water is very easy to absorb on the surface and make a very, very low performance for indium selenide electronics. As you can see, it's a foliation flag and the Raman spectrum like this one. Is the green line is foliate flag, but this peak will disappear very, very fast. It's because on the surface they create a lot of indium oxide on the top, something like this one. Okay, so scientists try to use a lot of methods to overcome this oxidation problem. So they think about maybe the oxidation problem is come from the substrate. So they use a PM membrane on the bottom of the indium selenide and realize the high mobility devices. Some people use the top surface preservation layer, so they can pin the bond nitride on the top. And then they can reduce his loop. And the other group use the hafnium oxide on preserve the top layer and realize the high performance devices. And there is also one group use the indium oxide safe growth indium oxide growth on the top of the indium selenide to realize the good performance. Okay. The challenge 2 is a metal indium selenide contact problem. As you can see, it's a band structure of the indium selenide. It's a work function for other metal. Some people believe they can use an indium to get the good performance. From the theoretical position, the people believe they can use a cobalt as a good metal for the indium selenide. Other group use a graphene contact on the as a contact material, contact electrode can get a very good performance. Or there is one group use a very complex the configuration to realize edge contact structure, and they can get a very good device performance. But then this structure is not easy to realize. Okay, so for our first topic, I try to introduce a new method and to realize high performance and low contact resistance indium cellular transistor. Okay, let's review the history of the mobility in this material. 7 years ago, people tried to make the devices and find the device mobility quite low, and as I mentioned, some people use a PMMA to increase the mobility. The same year, there is another group use the Hall effect measurement to get the temperature independent mobility. And 5 years ago or 4 years ago, try to use the dry oxide method to increase the mobility from the 50 centimeter square per volt per second increase to the 500 centimeter square per volt per second. Okay, we try to use another method. This method is called the surface charge transform doping method, SCTD method. We deposit the indium metal on the top of our channel, and also using this metal as our contact electrode. And this metal layer can dope a lot of electron go to our channel, and then we can get the low contact resistance as well as high mobility devices. It's a band diagram, as you can see. It's a Fermi level, and this Fermi level higher than the conduction band of our indium cyanide, and then dope a lot of electron in this interface. So this method, we can dope the channel, we can reduce the contact resistance, we can passivate the channel surface. So the device figure is something like this one. The thickness, we always select the 9 to 10 nanometer. Okay, so as you can see, like this one, in the beginning, if we don't deposit any metal on the top, we got a very large hysteresis loop, and the current is not very good. But when we deposit the metal, something like this case, we use the 32 nanometer indium on the top, and then we can get the small hysteresis loop and the high current and also high mobility. And then IV curve is linear. We try to study a temperature independent charge transport, and this charge transport, as you can see, the mobility increase and then saturate, and it has a loop reduce from the 20 volt down to the 0. The threshold voltage will also shift to the positive part. We also try to study the charge fluctuation mechanism, and we also study the steady state and the contact resistance. As you can see, our device can keep the performance more than 1 month. And from the statistical result, the mobility, average mobility is close to the 4,000 centimeter square per volt per second, and the on-off ratio is higher than the 10 to the 7 order of magnitude. It's very, very big. It's a indium thickness dependent device performance. As you can see, when you increase the indium thickness, the performance is the doping concentration increase and the contact resistance reduce. Okay, as you can see, contact resistance reduce. And we use this performance to realize, as you can see, we realize inverter function, we realize not AND and not OR function, shown here. Finally, in this part, we try to try to give you a figure. The y-axis is mobility, x-axis is unfold ratio. As you can see, the graphene is shown here because of the zero band gap. So mobility is very large, but the unfold ratio is very small. Organic electronics is shown here. The unfold ratio is very big, but the mobility is quite small. How about our case? Our case is shown here. Our case, we got the high unfold ratio, also high mobility. And this result is much better than the ITRS 2.0 low power requirement. Okay, it's the first topic. And the second topic, we try to develop the safe power trouble electronics. We publish this result on advanced function material. As you can see, these are our devices. We try to connect the trouble electronics, and we try to use the force, mechanical force, to reduce to create the power and then control our devices. As you can see, the different distance, we show the different power, and this different power can control our devices. Our device control like this one, the different distance for our trouble electronics, and show the different device current. And we also use this force to realize the Morse code, and also use this force to turn on the LED in our devices. Okay, it's a second topic. We try to develop a safe power trouble electronics. The third part, we try to develop the oxidation-induced charge trapping electronics. As I mentioned, the indium cyanide is ultra sensitive material, 2D material. So we, in our previous study, we try to put our device into the baking condition. So for the baking condition, the hysteresis loop is very small, like this one. But for the ambient condition, it's because there are a lot of water and oxygen on the surface, so the indium cyanide will absorb those oxygen or water and create a very big hysteresis loop. And we try to use this hysteresis loop to understand the physical mechanism and develop non-volatile memory devices. Okay, so as you can see, we try to use TEM cross-section to understand what is the reason to get this very big hysteresis loop. It's because there is a indium oxide layer on the top of indium cyanide. So this oxide layer, the thickness is about 2 nanometer, and this 2 nanometer oxide layer can trap and release the charge as function of the gate voltage. So therefore, we can control the loop size and realize the non-volatile memory function. So we use the low frequency noise to understand the mechanism. We also use KPFN to understand the potential variation. And finally, we can give you a cartoon figure like this one. There is an oxide layer, and this oxide layer can trap and detrap the charge in our channel. And then we can control the channel loop, and then we can control the threshold voltage shift value, and then we can realize the retention performance, endurance performance, as well as a multi-state storage function. Okay, so in this part, we try to realize artificial snaps. As you can see, in our previous case, we already realized non-volatile memory, and this non-volatile memory maybe can help us to develop artificial snaps. What is artificial snaps? I will introduce something. As you can see, now we are a lot of electronics in our life, and our electronics calculate a lot of data and put this data and go into the cloud. And in this cloud, calculate those data, and we download our data again. So as you can see, it's an energy forecast as function of a year. As you can see, every year the energy we need increase very, very fast. So in the future, if we like to develop or deal with those data, we need to more and more power. So maybe I need to say the big data maybe is a big energy challenge. So how to overcome this challenge? So let's think about the computer configuration. In our traditional computer configuration, we have CPU, we also have a memory, and we try to put our data from the memory to the CPU, and from the CPU also back to the memory. We lost a lot of energy in this bus interaction. So it's a serial operation process, also we call a non-Newman method. It's a traditional computer configuration. How about our brain? Our brain is like this one. We can, it's a parallel operation. We can computing our data, we can storage our data simultaneously. So this structure actually significantly reduce computing step and the process, and then save the power. So the goal is like this one. We try to use a digital computer to mimic the function in our brain, and maybe we can realize eco-efficiency electronics. As you can see, people try to do that. It's a digital computer with a lot of size and with a lot of power. If we use a silicon to mimic the neural, and we can reduce the power, also reduce the thickness. We also reduce the size. But this scale also much larger than the biological neural. So we try to use our devices. As I mentioned, our device can realize non-volatile memory. So this non-volatile memory structure can connect to the snap. Snaps is a very important component in our brain. So we use the gate voltage as the input spike, and we try to observe the PSC value. So as you can see, the different gate voltage, we can control the PSC value, and the different pulse width, we can realize the EPSC. We also can realize the IPSC, and something like this one. And we also can realize perturbation or depression function, and also realize accessory SNAPs function and PPF function, and then recognition rate we also can realize. Okay, and we also take our device. We also use a light to. We also use a different wavelength light to expose our device, and then we find there is a very obvious precise photocurrent like this one. However, if we change the substrate, the precision photocurrent will reduce significantly, and then we try to use this precision photocurrent to create other interesting SNAPs function. Okay, so what is the reason to make this precision photocurrent is also the reason is also very normal, is because people always know, it is well known, if we put the 2D material on the silicon oxide substrate, there are a lot of electron hole particle, and then this electron hole particle can be changed by tuning the potential in the substrate. So as you can see, the backgate voltage is -10, from the -10 tuned to the 55 voltage, and then the potential is totally different. So we try to use the backgate voltage to tune the potential particle, electron hole particle, and then we can get the new SNAPs function. As you can see, it's a precision photocurrent under the negative gate voltage, and under the positive gate voltage, the change is totally different, and then we can this gate voltage is tunable, and we can gather the different feature of our precision photocurrent, and the Runyin result may be like this one. And this result is because when you tune the backgate voltage, we can trap electron, we also can release electron, and the trap and the release process, we can gather the different precision photocurrent. We also use the low frequency noise to understand the detail. And we try to use the live photo as our pre-spike, and to understand, try to measure the response of our devices to mimic the snaps function, so we can realize short-term persisticity or long-term persisticity, and we try to use different wavelengths to gather the different precision photocurrent. We use the different power to gather the different precision photocurrent. We also use the different pulse width to realize the precision photocurrent. Okay, and then finally we use this gate effect to realize the one key feature for the short-term persisticity is called PPF, pair path precipitation. As you can see, if we give it a true pulse go to our devices, if this pulse difference is very short, and if this pulse the pulse interval is shorter, the second response will be higher. So therefore, in our device, is a pulse the interval is a pulse interval is increase, the response will be decreased. Okay, like this one. But if we tune the gate voltage, this feature will become the featureless and then become the inverse feature. So from this inverse feature, we can tune this PPF behavior. So this PPF behavior, as you can see, we can connect to the older guy and the young guy. For the older guy, the learning efficiency will decrease as a function of the rehearsal interval, something in the older guy. The young guy, they can increase as a function of the rehearsal interval. So we try to create a new function for the snaps. In the final story, we try to use our device to mimic the drug dosage modulation, something like this one. We publish our paper to the MPJ 2D material apply, and also publish it to the advanced function material. So we also use the same backgate voltage to tune the future, to increase the precision photocurrent and the decreasing precision photocurrent, and realize the drug modulation function. So I try to use a very short time to give you a conclusion. We can dope our devices. We can dope our devices. We can understand the mechanism, and we can develop the safe power electronics. We also can realize memory. For the neuromorphic electronics, we can realize artificial snaps. We can realize inverse PPF. We also can realize the drug modulation. If you are interested in our work, you can review our advanced material, advanced function material, natural communication, neural engine, and so on. Okay. Finally, I thank you all for the members to work in my group. They are very nice and work very hard, and then we just can get this interesting result. Thank you for your attention.
Okay.
Thank you, Professor Lin. Just an announcement, I want to push you to visit the Padlet wall and post comments or question for the various delegates of this bilateral meeting. There are 25 virtual stands with 20 institutions, with over 200 posts with videos, posters, website, scientific papers, podcast contribution. So please visit the Padlet wall and post comments there. We are very late in Taiwan. It is night now, so Carlo, please finish this this session.
Okay, so, I want to thank all speakers and the ambassador of Taiwan in Rome, Davide Giglio, chair of Italian Economic Trade and Cultural Promotion Office in Taipei, the Deputy Minister Min Song Lin, and our Rector of University of L'Aquila, Eduardo Alesse. Thank you, everybody, and thank you for your attention. Do you want to add other information, Antonio?
Tomorrow we will start at 8 o'clock in Italy, so 7 hours later for the different time zone in Taiwan. So see you tomorrow, and in the meanwhile visit the Padlet wall. I hope to see your comments.
Bye bye. Have a nice day. Bye.